Okay, good morning again. So I'm going to talk about aerospace materials, okay, and fatigue and fracture. Should I point it there? So, okay, the four materials classes that of interest to this lecture would be aluminum alloys, okay, 2000 series, 7000 series, aluminum, magnesium, silicon type of alloys, which are 6000, okay? And most of them are wrought alloys for the aerospace. We do make some cast aluminum alloys, but they have but we have a problem with the castings for aerospace because we don't know how to take care of the casting factor, because there is too much porosity and too much this of that. But the automotive companies do like cast aluminum alloys because they're much easier to make, right? But we'll talk about them also. And then the other class of materials are titanium alloys, both alpha beta titanium alloys, near alpha alloys, and lately there have been some good beta titanium alloys that are coming along, so we're interested in them also. And I'm following the technology as it's moving, okay? And yeah. You'll be getting notes. Actually, it's my fault. I did not give these things to Amit in time. But we will provide you with the copies of all these, okay? And yes, definitely, yes. And I'll try to do it as soon as I can so that you don't have to wait too long. He wanted to put everything together in one place, so that's what is taking time. And you know how we are, we wait to the last minute. And I'm one of those. Okay, so aluminum alloys, titanium alloys, then you see very high strength, high fracture toughness steels, which are especially used for landing gear steels, because we need both high strength and high toughness. We need both, okay? So things like alloys like 4340 steel, Maraging steel, and very recently there has also been some stainless steels that have come along for landing gears. From Chicago, from a company, Greg Olson. Greg Olson is the person who has come along. It has been tested. I'm not going to talk about that much, but it's a stainless steel that everybody is slowly buying into. Everybody is trying to wait and see how the whole game is played. How the industry is. It doesn't pick up new materials right away. There's too much of hassle involved, certification, and all that stuff involved in the new materials, right? The nickel-based superalloys, which are used a lot in the aircraft engines, turbine engines. Of course, I'm talking about the aircraft turbine engines. The same thing applies for the land-based power engines also. The same technology, okay? The only difference is, in the case of the aircraft, you need lighter materials. You cannot, so we stay with nickel-based superalloys most of the time. Even though cobalt-based superalloys, iron-based superalloys will give you better properties, but we can't use them on the aircraft because they're too heavy, okay? So we stay with nickel-based superalloys. So those are the four classes of materials that I will stay. Most of my examples will essentially encompass those four materials, okay? And then the couple of secondary operations that are very critical actually are welding. I heard a lot of people are doing friction stir welding. And then the manufacturing methods. Unfortunately, throughout my career in the aerospace industry for the last 30 years, one thing I have seen is whenever we are developing new materials, we always ask the question, what should be the strength? What should be the fracture toughness? What should be the fatigue crack growth? But we never ask the question, is it weldable? What kind of properties are we going to get after welding? Can we manufacture it? Can we manufacture it in a cheap way? We don't ask these questions. We only ask these other questions, mostly relating to structural integrity, right? But we don't ask these questions. But I think we're all realizing that's a mistake. We need to ask these questions up front. Like the commander was talking about, can I have maintenance-free materials? That's a very, very important question for people like us. It's very difficult to make that. He's got a very, very intelligent question, which is a very difficult question to answer, okay? And then once you know these things, this information, this knowledge, and how to evaluate things. I saw somebody was talking about fatigue analysis of epoxy patched aluminum skin, right? Somebody was talking about that. Who's that? Raise your hands. Somebody, you were talking about fatigue analysis, right? Fatigue analysis of epoxy patched aluminum repair, for instance. How does it perform? Yeah, exactly. So those are the things that are very important actually when you're talking about maintenance, when you're talking about life cycle maintenance of aircraft. These are all very important questions, okay? And so when you're gathering your knowledge and information on processing the material, what kind of microstructure would you get? What are the properties? You should also ask these other questions. Is it weldable? Can I do it? Can I do solid state welding, like friction stir welding? Can I do fusion welding? If I do weld, how much am I going to lose properties wise? Those are all important questions from a design point of view. So when you go to the industry, one of the things you have to do as a materials engineer is to always talk to the design guys. What do they want? You should always work with their needs. What do they want? Then you come back to the lab and do the things to what they want, okay? So we'll go along with this, and then okay, let me see. Should I? Okay. The next slide is going to give us some. The next slide, I kind of put an Excel table just to show you these aluminum alloys, titanium alloys, steels, nickel-based superalloys. What is the operating temperature range of these materials? Because depending on the operating temperature range, you want to select your material, right? You want to fabricate your component or your structure from one of those classes of materials, depending upon what is the operating temperature range. But that's one criteria. And then, of course, we'll talk about I'm going to start from the very basics, because Professor Arora was telling me there are some people who may not be even familiar with some of the basics before we jump into fatigue and fracture. So I may just spend about one lecture, about an hour or so, just getting into the basics of mechanical properties, tensile properties and impact test and those kind of things. And then I will talk about the failure modes, which are important to understand: ductile fracture, a brittle fracture, intergranular fracture, those kind of things, cleavage and those kind of things. Because these are very important, even though we don't come across this fracture that much anymore out in the field in real applications. We don't come across cleavage fracture that much anymore because we know how to design against cleavage. But it's a very important part of the evolution of fracture mechanics. The whole fracture mechanics started because of this low temperature fracture mode cleavage. I'm going to show you that a little bit, okay? And then I put here a cartoon basically showing you when we are talking about operating temperature range of structural materials. If you take aluminum alloys, like for instance, 2000 alloys, 2000 series, like 2124, 2024, 2219. Actually 2219, and today of course aluminum lithium alloys, they were used by NASA to fabricate the yellow-orange, the big tank, right? The big tank. And there's a lot of friction stir welding that goes into this dome that you see. And this dome is made by spin forming. I was involved in this personally. I was involved in this research, so I know more about it. So I kind of put this up because some of you are working in friction stir welding. And I wanted to show you that friction stir welding is a very, very important technology today. We started friction stir technology just about, I would say, maybe 23 years ago, back in the United States. It came from TWI in Cambridge in the UK, and we brought it to the States afterwards. So friction stir welding technology is a very important tool today. But we did all the aluminum alloys, but we're still struggling with titanium, I think. And of course, nickel-based superalloys, joining of nickel-based superalloys is a little bit hard because we don't have the right tools, right tool bits, right? And then let me put this one. Okay, so this is something I put down here. So when you take from room temperature to 150 degrees Celsius, actually you can even go to cryogenic temperatures, because I just told you that aluminum alloys can be used for the cryo tanks for space launch, right? Anytime you have an engine, you need two things, right? One is an oxidizer, the other one is the fuel. There are two things that you need. Like in your car, for instance, you pick up the air from the outside and you combine it with the gasoline, right? And you produces the thrust that you need to go forward, right? The same way, even the space launch, you need liquid oxygen as your oxidizer and liquid hydrogen as your fuel. The two combine and give you the thrust. So that's where you use the aluminum lithium alloys for your cryogenic tanks. So aluminum alloys, you can go up to 300 degree F. But one thing I put here, you always have to ask not just what temperature you're going to operate, but how long are you going to operate and what is the load that is important. That's the important thing. You know, I mean, I can always use any material for n number of hours, but if there's no load, yeah, there's no problem. You know, but if there's no time limit, you know, then it's no problem. But once I put the constraints, I want to use it for 1,000 hours. I want to use it under this load, then things completely change. The whole picture changes, right? So that's aluminum alloys. Magnesium alloys. We use magnesium alloys mostly for pistons, okay? Mostly for pistons, mostly for oil carrying containers, hot oil, okay? So whether it trucks, cars, even airplanes, where you have hot oil, you know, up to 400 or 500 degrees Fahrenheit, then you're going to use your magnesium alloys, right? You don't use aluminum, you use magnesium. But the only problem with magnesium is it corrodes very, very easily, but not when you're using for it hot oil. There's no problem, okay? And then, of course, the most important one, the titanium alloys, right? The titanium alloys, you can go up to, you know, 1100 F is a little bit too much. I would say up to 900 degree F, you have to convert this into Celsius. I'm more used to the Fahrenheit, okay? We don't like to change to Celsius yet, so like somebody was talking about, when you were talking about the beta titanium that you're working on, you were working on alpha beta, right? Alpha beta titanium? Oh, you were working on alpha beta titanium. You're working on what? Aluminum? Thermomechanical processing of steels, okay. From IIT Bombay, right? Yeah, that's what I remember. Okay, so titanium alloys, you can have alpha beta titanium alloys, which are, those are the workhorse alloys. That means we use them all the time. The titanium 6-4, mill anneal titanium 6-4 is used everywhere. It's the most common titanium alloy, which has got both alpha phase and the beta phase, okay? And we'll talk about a very interesting phenomena that takes place in titanium alloys, which is called as dwell fatigue, D-W-E-L-L, dwell fatigue, which is actually a big problem with titanium even today, even till today. It has never been solved. We never can understand what is the real basic scientific issue behind dwell fatigue. And I'm going to spend a whole lecture on it because it's a very, very important technological problem, okay? Which has not been solved yet. Okay, then we talk about these up to 1200 degree F. We talk about stainless steels. We use very little stainless steel in the aircraft. But if you go to the chemical industry, if you go to the chemical plants, we have a lot of stainless steel tubing, 316 stainless steel, 304 stainless steels. A lot of it is is used actually, okay? And then of course, we talk about our, oops, let me just go back. Oh. Okay. So then we were talking about the nickel-based superalloys, which are used in the aircraft engines. I thought I had here. See this thing, this picture that I put up? This is a small section of the turbine engine, okay? This is your fan. This is your fan section. So, and there is your compressor. After that, there is your compressor. Okay, and there is your combustor right there. There is your combustor. So the fan, so this fan is made of titanium 6-4. Most of the fans. But now today we are moving to composite fans. Some General Electric turbine engines are using composites. And also there is also push for using aluminum lithium for the fans, okay? So what does the fan do? The fan sucks the air from the outside, and then this compressor after that, it compresses the air, all the air that is sucked in, it compresses the air, and then it goes and combusts right there in the combustion chamber with the aircraft fuel, which is JP8, jet propulsion number 8 fuel, and then it produces the ignition, and you turn your turbine engine, and then exhaust from there. So basically, that's all what turbine engine is. I'm making it look very easy, but that's what it is basically in different, fan, compressor, combustor, turbine, high pressure turbine, low pressure turbine, and exhaust. So those are the things. So you're using your titanium alloys right here. These fan blades, this fan disc, this whole disc, okay? This whole disc here, the casing, these are all titanium alloys. Very, very important function. Turbine engine, all nickel-based alloys. Part of this compressor, the back side of the compressor is all nickel. The front side is all titanium. So these are all very important materials from a turbine engine point of view, because this machine rotates about 30,000 revolutions per minute. 30,000 revolutions per minute. So you all know centrifugal force, right? In high school physics, if you put a rock and if you do this, there's a centrifugal force. So basically, when this is rotating at 30,000 revolutions per minute, these blades want to come out because there's a force acting on them. The blades want to come out of the root, right? They want to come out of the root. And now if you have high temperature, you're going to have creep. Okay? So it's revolving, there's a centrifugal force, there's a temperature, so there's a creep. There's a tensile creep. So there's a creep elongation. Creep elongation. Very important, creep elongation. Because from a performance point of view of an engine, this gap between this casing, I'm not showing the entire picture, I'm just showing a cutoff. The gap between the blade, the end of the blade, and the casing has to be very, very narrow, very, very small, so that, but that's how it is in the computational fluid dynamics. It tells you that the gap between the blade and the casing, the smaller the gap, higher the performance. So the design engineer is always trying to make that gap smaller and smaller. But as a materials engineer, you're having the problem of creep, where the blade is going to creep more, and it's going to start touching the casing. It's going to start rubbing the casing. So there is a, you have to balance the two. So as a materials engineer, your problem is extraordinarily difficult because you have to make sure that your elongation is just right so that you get the maximum performance, but your blades don't get stuck in that casing, right? And today, for instance, can everybody see this? So here's the Boeing 787 today, the latest and greatest, right? Airplane, right? Oops. We are using about 47% nickel-based superalloys, 47% nickel. We're using about 25% titanium, 8% aluminum, 4% composite. This composite is all polymer matrix composite. I don't think it's metal matrix composite so much yet. We are not there yet, but it's being introduced. It's being introduced. The introduction of materials is always done from the military side first, and then it comes to commercial, always. because the military can take, they got the money, and they can also take the risk. If something's, if a plane falls down, okay, no problem. So what? We'll buy another plane, right? But in the commercial side, you can't afford that. Your 400 people are sitting in that plane. You cannot say, okay, let the plane fall, I don't care. No, you're going to care because 400 people's lives are involved, right? So you always want to try your new material on the military side, and then when it functions good, you bring it here. Now, why did I say that? I said that because metal matrix composites, I don't want you to think that metal matrix composites are not important. They're very important, but they're being introduced, they're being flown in military aircraft. They are going to come to commercial. It's going to take a little bit of time. They're not there yet, right? Because you have to build long, big parts, okay? And then you have to certify them that they can function in the sky for such a long time. So that's the important thing. Okay? And then you got some iron-based, 16%. I think this is all weight percent. I don't think it's volume. And I'm not sure, actually, come to think of it. Okay, I may have to check on this, whether it's volume distribution or it's a weight distribution. So 16% is iron-based, like we talked about the landing gear, for instance. It's all landing gear steel, right? I mean, it's a very, very high strength, high toughness, because you're bringing the whole plane down and it has to withstand the weight, right? And then you got that. Okay, so I just wanted to emphasize why these materials are important because of this. That's why these materials are important, okay? And even though these are aerospace materials, but they're also used in the power industry, land-based power engines. They're also used in the, somebody said they're from the nuclear industry. Nuclear industry. Of course, the nuclear industry is zirconium-based, right? A lot of it is zirconium alloys. But some of these alloys will be used for the other industries as well. And the space, the same thing. You use a lot of these materials for space launch and liquid rocket engines, solid rocket engines, everywhere. So these are all pretty much standard aerospace. Even though I call it as aerospace alloys, you can call by different names. Like the commander was talking about, what is the payload of a helicopter? Did he say 5 kilograms? 50 kilograms. 50 kilograms. 50. That's a lot. Okay. Huh? Oh, okay. Yeah. So he emphasized the fact that how important it is to even raise by maybe half a kilogram or 1 kilogram payload. It's very important. So a lot of times we call these, the aluminum and titanium alloys, as lightweight materials. Because if you can design your components out of aluminum, titanium, and composites, you can increase your payload. Because you're going to make your structure light. That means you can put more payload. That's why it is so important. So they fall under the class of lightweight materials because they got high stiffness, low density, high strength, high tensile strength. Right? Okay. We'll come to those things eventually. Okay. Payload, okay, payload, for instance. I can tell you in terms of space much more easily because I'm involved there. So if I'm taking a satellite into the sky, into the space, that's my payload, right? Because I have a gross weight of the rocket without nothing. I got the fuel weight is there, right? And the other structural weight is there. So if I had to take a satellite, that becomes my payload. So when I'm going into space, the stage 1 rocket takes me to outside the Earth's gravity, right? I go up to there and I drop the rockets into the ocean. I drop them. I don't need them anymore because I already burned my liquid oxygen, liquid hydrogen. They're burnt. I don't need them. So I drop it, right? But unfortunately, when I'm on the land, I have to consider the weight. So I should make it out of a material that's very, very light. And that only has to withstand for 10 minutes maybe, or 8 minutes. That's it. Because once that 8 minutes has passed, that job is done, right? So I have to take those into considerations when I put my payload. Anytime I can lower the weight of the structure, I can add more payload. Back when I was working in space, maybe 98 or something, for every 1 pound or half a kilogram, right? For every half a kilogram, it used to be $15,000 to take it into space. So if you want to put something on my rocket, on Elon Musk's rocket or my rocket, I don't have one, I'm just using it as an example. Or I want to put on your rocket, half a kilogram. I have to pay you $15,000 to put my stuff in your rocket. That's how expensive it is. But in order to do that, you have to have less weight on your rocket. So I gave you a long answer for a payload. Okay. So here's some comparisons of elastic modulus. You'll be surprised when we design aircraft. This is one of the key things. This is one of the key elements, because when you want to find out your specific modulus, you take these numbers and divide by the density. That's important, okay? So here's a comparison. On the Y scale, we have got gigapascals, elastic modulus. And then here you have tungsten, pretty high, 400. And here you have magnesium, very light. I'm just giving you a comparison here. Magnesium, aluminum, silver, it keeps going. Steel and nickel, molybdenum, tungsten. Steel and nickel are right about there, about 240 GPa. And here you have about 40 to 43 GPa here. And then here you have diamond. Diamond is right there, pretty high. High elastic modulus. Graphite is right there. This is the pencil that you use, right? Graphite is right there, soft. There are your carbon fibers. Now, the people who are working in composites, who's using carbon fibers? Anybody's using carbon fibers? You're using carbon fibers, okay. So there is your modulus for the carbon fibers, okay. I thought I put here, okay, glass fibers. We use some aramid fibers, we use quite a bit. So they're all, just a comparison. So you'll get this. I'm going to give you, this will be in the package, okay? Okay. There is your yield strength. So we talked about modulus. There is your yield strength comparison. So there is your landing gear steel right up there, very high. Actually, it's 4140. We have better steels than that, actually. Even though 4140 is a very good steel for landing gear, but many of the landing gear steels are right up here, right about 2000, okay? Very high, very, very high strength. But you have to remember one thing. I'm just giving you some data as I'm going along. Higher the strength of the steel, it's more prone to hydrogen embrittlement. Hydrogen embrittlement and yield strength always go like that, okay? More strength, more possibility of hydrogen embrittlement, unfortunately. Nature always plays these games with us. So we have to play the games back, right? Or at least we have to listen to the nature and provide the solutions, right? And there is your titanium after that, okay? Aluminum is right there, wow. There is your 6061 aluminum, sir, your waveguide, 6061. I don't know if I'm supposed to say that waveguide. Is it? Yes. It's okay? Yes. It's nothing classified. Okay. Okay, so there is your, oops. Yeah, there is your 6061 aluminum all the way down there, strength-wise. And the steel is way up there. Big difference. Almost factor of 6, huh? Or 60. Not 60, but 50, yeah. And some polymers here. I'm not a polymer guy. I wish I was a little bit. I wish I knew a little bit about polymers. I know some of these things, but not very well. PVC, PVC pipe, polyvinyl chloride, okay? And but these are very useful, useful graphs, actually. They're very useful, especially if you're trying to invent something. If you're trying to invent something, one of my, not my friend, I mean, one of my, he was taking a class from me, actually, and he's an inventor. He's only an undergraduate student. And he was telling me he was coming up with something in the back of the car so that when you brake the car, not necessarily only the lights that you see, but he wanted to put a strip, a plastic strip, which will also light up. I don't know why he wanted to do that. So he was looking for a material which has got a good modulus, which won't just kind of break when you do this, but at the same time be able to bend it. So, and he's selling a lot of those things now. In Canada, he was able to find the market and he's selling. So I gave him this graph to see if he can use it. So sometimes these kind of graphs are very useful. If you're not a materials guy, but you're thinking about some of these things, thinking of making a new invention, they come very handy. Okay, tensile strength. Again, that 4140. Yield strength, tensile strength. Right? There is your diamond, very hard, right? Diamond, and then there is a graphite, aluminum oxide. How many of you have polished materials in the lab? Metallography polishing, right? Yeah, some of you have done that. So there is your aluminum oxide that you use, that white powder or the white thing. There is your aluminum oxide, which is a very important ceramic, actually. It's a very important ceramic. Not necessarily only for polishing, but it's used in other places too. Silicon nitride. Yeah. So all these things, and then here is your polymers. Here is your composites. Okay. Okay, I'm going to change the gear now a little bit. How many of you do not know? Don't be embarrassed. It's okay. Like I said, I don't know anything about polymers. No big deal. How many of you have never done any tensile test or do not know tensile properties, what they are? If you don't, I will go through it. If you do, I won't go through it. Do you want me to go through it? Huh? How many of you want me to go through it? So yeah, just a little bit, just go over it. Just go over it. Okay, just go over it. Okay. So here's a typical tensile testing machine. I mean, it's an important machine, right? So there is your load cell. It's calibrated to different kilograms, newtons, pounds, right? And here is your tensile sample, tensile specimen. You can measure the elongation in the specimen using this extensometer. Using this extensometer. It's basically a linear variable differential transformer, LVDT, that's measuring the elongation in the material, right? And this is moving crosshead, but this is an old machine. These days, the machines are all servo-hydraulic machines. They are not screw-driven machines like this one. I used one of these screw-driven machines. Okay, so, there is a sample design. There's a sample design. Sometimes when you want to design a sample, you don't know where to go. It's such a simple thing, but you're looking for measurements everywhere, all over the place. So I thought I'll put one of these here. Simple assessing ductile brittle behavior via simple tension test, right? So here is a very ductile material, right? You got yield, somewhere here, yield point, 0.2% offset yield stress, and then it work hardens. You got the ultimate tensile stress, and then it goes down, it necks right about there, and then it fractures, right? So that's a pretty ductile material. So here is a comparison of ductile and brittle. Obviously, the brittle has got much higher yield stress, but much lower elongation. So this is my strain or elongation. Doesn't matter, same thing, right? If my gauge length is 1 inch, my elongation is same as a strain because I divided by the original gauge length. So there is my brittle behavior, there is my ductile behavior. In the old days, before you guys were born, even before I was born, people used to measure toughness using these curves. They would measure the toughness under the curve, stress multiplied by strain essentially, d sigma d epsilon dot, right? Area, Yeah, area under the curve. You plot that on a green graph paper with squares and you count the number of squares. Yes. That's the area. Right, that's what we used to do, right? Remember? Yes. Okay. Typical stress strain curve, you know, for those things. So, yeah, pretty good, right? Okay. Oh, yeah.
At the point of tensile strength,
yeah,
we are applying the load, and load is constantly increasing.
Mm-hmm.
Then why stress is decreasing?
Because see, up until here, the cross-sectional area is decreasing, right?
Yes.
Yeah. So here, you don't need that much load anymore because the material is not able to sustain any more load.
So we are decreasing the load.
Yeah. So even though the elongation is going up, remember the crosshead is still moving. The crosshead is still moving, so that's why it's like that, right? Yeah. Because the load is falling down also, even though the cross-sectional area is decreasing, but the load is falling at a much faster rate than the decrease in the cross-sectional area.
But in the UTM, we keep on increasing the load.
No, it only increases up until here. Oops. It only increases up until here. Okay? Then after that, no more. Okay? So, you know, I mean, just some pictures here. Basically, I mean, this never happens, but this is a very common, I mean, idealized behavior where things are necking and all the stuff, you know, to a point. Things are necking. Let's look at this one. Modulus change with temperature. Elastic modulus really doesn't change that easily. It does not. It's one of the most difficult things to change. So there's a good change with temperature. But if you want to do alloying and change the modulus, not much. You're not going to change much. Except in aluminum lithium alloys, yeah. Elastic modulus, yeah, because the springs would become, yeah. The springs, if you consider it as two atoms and there's a spring in between, the stiffness would fall down. Yeah, exactly. Yeah. So as the temperature is decreasing, the spring is getting tighter. You're right. Yeah. In body-centered cubic materials, this is a very, very specific, very unique property of body-centered cubic materials, like iron, vanadium, steel. Aluminum is face-centered cubic. Yeah. Body-centered cubic materials like iron, vanadium, beta titanium. Okay? Those are all body-centered cubic materials which show a very, very strong effect with temperature. Their yield strength changes very strongly with temperature. So lower the temperature, higher the yield stress in the case of body-centered cubic materials. So lower the temperature, higher the yield stress. It does not happen so easily in FCC materials, but in aluminum lithium it happens. Aluminum lithium it happens. That's why aluminum lithium is so unique. Yeah, so unique material. So here you can see a comparison, room temperature, -100, -200. This has got, you know, people used to produce PhD theses out of that back in 1970s. If you look at the literature of body-centered cubic materials, there is a whole bunch of literature on this phenomena of temperature or the yield stress effect, temperature effect on yield stress. Thousands of PhDs actually, I would say, at least 500 PhDs, if not 1,000. Okay? It all has to do with the chiral stress, inherent chiral stress of the, this is a totally different topic, which we don't have time for, but yeah. The dislocations have a hard time moving up the barrier, essentially. But that's a very important phenomena in body-centered cubic materials, temperature effect. It's got a lot of implications in real life. Yeah, ductile material, basically just showing some couple of pictures, nothing much. Oh, okay. So here, effect of, I think this is Actually, effect of cold work on tensile properties. It's like work hardening. So if I take a material and put some cold work, so if you have a tensile sample, if you put some cold work into it, and now you put back into machine and do it, its strength will increase. No big deal, right? So it's considered as one of these strengthening mechanisms. Work hardening is a strengthening mechanism. Okay. So for different materials, this x-axis is percent cold work. So if I put in more and more cold work, your yield stress keeps on increasing in these materials. Copper, which is an FCC, brass, FCC, 1040 steel, DCC. So this happens in both body-centered cubic as well as face-centered cubic materials. Okay. This has got a lot of implications in processing. So if I am trying to extrude a material or trying to, what do you do in your case?
Cold drawing.
Cold drawing, for instance, it's a very important thing. So I cannot take a material which is already cold work because it will become much harder to draw it as a tube, like he does. But so that's what this is. So it's got a lot of implications to the processing aspects. So if you put more cold work, it's more difficult to do the processing because the yield strength has gone up. Okay? So these are all the things that interplay in materials. You know, there are too many things going on, you know, really, when you look at it. The rest of it is. So you can put cold work. One important thing I want to tell you, you can put cold work using the rolling process, or you can use a tensile machine. Okay? If I take a blank piece of material, I take a blank piece of aluminum, solution heat treated, it's very soft. Okay? And I put through a rolling mill and I put 20% cold work on it. What I'm doing actually in terms of dislocations is I'm increasing the dislocation density by putting cold work, right? I can do tensile deformation, or I can put through the rolling mill, and I'm putting dislocations. So when I take that material and do a heat treatment on it, age it. In aluminum metallurgy, we call it as aging the material. All we're doing aging means we're putting it in a furnace at a certain temperature to precipitate, to make precipitates so that those precipitates will give you strength. By doing the cold work, I'm putting dislocations into the material, which will act as the nucleation sites for the precipitates to form. And I will get a very uniform precipitation, not just isolated here and there. So in some alloys, aluminum alloy metallurgy, when we are doing the processing, we do put some cold work. And then we do the aging so that we increase the volume fraction of the strengthening precipitates so that the strength will go up. Because the strength is proportional to volume fraction of the precipitates. So it has got another implication in the business of processing, microstructures and processing. Okay? Okay, I'll wait for that comment. Okay. Oh, yeah. I'm actually seeing here two pictures. So, I mean, it's a very simple thing. There is your brittle behavior, right? There's no necking, nothing, flat surfaces, you know, the thing broke essentially, right? Oh, here, so there is your brittle behavior. There is your deformation on a single slip plane. I mean, a single slip plane system, not single slip plane, single slip plane system. Because if it is face-centered cubic system, it is 1-1-1 slip plane, right? The slip plane in the, we have a pen here. Oh, yeah. So if we have a face-centered cubic structure, right? So there is my 111 plane. There is my 111 slip plane. My atom here, my atom there. Okay? And there is my, let's say, okay, so there is my 101. There is my other slip direction, and there is my other slip direction. So let us say this is 110. This is my 011. About, just about, okay? So there is my slip system, a slip plane and the slip directions, right? So if I am doing, you will see this later on. So when we say that when I'm deforming the material under tension test, and all the dislocations are moving in that one direction, they're all moving on that slip system, 111 in the case of face-centered cubic material, 111 slip plane. Okay? This becomes important when I won't say it now, we'll come back to it. Okay, I don't want to put too much information. So that is one interest, a single slip plane. Number 3 is ductile FCC materials such as pure gold next to a point. Okay, so here I wanted to, I know why I highlighted this. I was wondering why did I highlight this? So when you have slip in this single slip system, that is called as planar slip material, planar slip behavior. You will encounter this term a lot in the literature if you're doing your PhD or something in this area of nickel-based superalloys. Anytime a dislocation is cutting a precipitate, for instance, shearing a precipitate, and if it's going along that one plane, it's a planar slip material. When you have multiple slip systems acting, so I have this slip system and another slip system like this, right? Another slip system that is crisscrossing it. That means 2 slip systems are activated. You can have multiple systems activated. That is cross slip behavior. So this is planar slip. That is cross slip, multiple slip, cross slip. They're all the same words, They're all the same. The terminology is so screwed up. It's every field is the same way. Everybody uses their own term, and you think, what is it? You start going back into the literature and trying to find out what does this mean. It's the same thing, but you write multiple slip, I write cross slip. It's the same thing. I like to write cross slip. I don't want to use multiple slip because he used it already, the term. I want to copy him, right? But you're putting all the students in trouble. Okay, so that's what it is, right? And then you also have this. The other type of a fracture, which we'll talk about, is this kind of a void, a cavity that forms, okay? This kind of a cavity that forms, okay? I'll show you the next picture, hopefully. Yeah, hopefully there it is. Professor Arora, how are we doing on time? You have time, right? Okay, let me know, just let me know. Okay, so let us say I have a material which has got a lot of inclusions, another term now coming up, inclusions. See, that means the same thing as when I was trying to understand this, it took me a long time. I'm giving it to you freely. That's my job, to transmit the knowledge that I have. Inclusions. Because I was so embarrassed to ask other friends of mine, what this inclusion, what does this mean? It's the same as constituent particles. constituent particles, which is the same as second phase particles. Which is the same as, I'm going to use a dirty term, junk, dirt. Okay, just be careful, don't use it anywhere. Junk. Really, that's what it is. So these are the same things. Constituent particles, inclusions, second phase particles, people kind of, the same thing, you know. So here is an example of a material that has got a lot of these inclusions, constituent particles. So those are represented by these dots, okay? And why are these inclusions there? They're there because, let us say I take aluminum alloy, okay? There are elements in aluminum alloys like manganese, chromium, which are there in small amounts, and they form intermetallic compounds like Al6Mn, Al20Cu2Mn3, okay? Let me write those things down. Example, Al6Mn, Al20Cu2Mn3, or let us say chromium containing or chromium rich particle. If you don't know the exact composition, just say manganese rich particle. You don't have to know exact stoichiometry, manganese rich particle. Since I don't know the formula, I'll say chromium rich compound. Okay? I'm going to cheat. Chromium rich compound. Huh? Yeah, Al6Mn? Yeah. Okay. Al3Zr? Yeah. Okay, there you go. Cr23C6. Right? Cr23C6. Okay. So these are unwanted particles. Okay? You really don't need them, but they form at high temperatures, very high temperatures. So they're not going to melt again. Once they form, that's it. Their melting point is way high up there. They're not going to melt, they're not going to melt down. So these appear as these inclusions in this material. So when a material is deforming, they form these voids. Voids nucleate around those particles. And when you're pulling, the material around that void is stretching. Okay? So the void is growing. This void growth. Void growth. So I have particles like this. 1, 2, 3 like that. There's a void. This is stretching, and then they link up. They link up. Okay? So nucleation, growth, and coalescence. Nucleation, growth, and link up. Typical ductile fracture mechanism. It was worked in the late 70s by great guys like McClintock and those guys. Fred McClintock from MIT, of course, he's dead now. You know, that's what happens.
Due to that void, the edge is blunt, no? How can the crack tip grow? When the edge is sharp, stress will be high.
Yeah.
Then only the crack faster.
Right, so you're talking about fatigue.
Yes.
This is static. This is like a fracture toughness. You're right about that. When it comes to fatigue, it cannot grow if it becomes blunt. It has to remain sharp. But this is an example. So what I did here is, this is a uniaxial tension. This is like a fracture toughness sample with a crack in it. As you're pulling it, yeah, that's what is happening. Okay? But you're right. When it comes to fatigue, you're absolutely correct. Yeah.
Our country, we are saying
Yeah.
that get the material which is good, make the alloy, and after making the alloy, they give it a process called extrusion.
Okay.
And
To break it down. Yeah, go ahead. Yeah.
to do the extrusion.
Yeah.
Now when they do extrusion, they find lot of problems. Because when we are casting the material, the precipitation of the alloy is not very uniform.
Right.
So what they do now, those who are making good product, what they do after casting, they do a process called homogenizing. By homogenizing, all ingredients are distributed very nicely.
Absolutely correct.
And then this process is not happening in our material. Good and the defects. So this is highly.
Yep. I was going to come to that in the next lecture.
Yes.
But thank you for introducing the topic. Very good. Very good. Perfect. Perfect. What he said is absolutely correct. So we take the, okay, we'll come to that lecture. So remind me about what you said. Perfect. Very good. So that's why I put as junk. Dirt. That's why I put as a dirt, dirty material. It's got too much junk. Have you ever noticed, if you want pure aluminum, if you call somebody and say, you know what, hey, I want 99.99% pure, he will ask you how many nines. Is it 4 nines? Is it 3 nines? Is it 2 nines or 1 9? The more number of nines, the more expensive it is to take out all that junk. Okay? It becomes more expensive. So if you want a very pure aluminum, or not only aluminum, gold, any of the elements, the more purer material you want, the expensive it is, because you have to take out the junk out, right? But this junk is a little bit different, as he's talking about. We will talk about that. It's a very important point. But for now, just remember that this junk, big particles especially, these are big chunks. Big chunks means 25 microns, 30 microns, maybe 50 microns, like that, okay? Yeah, in the old days, it used to be like 75 microns even, okay? So let me just, okay, so when you look at this process under a scanning electron microscope, this is what it's going to look like, microvoid coalescence. So there are the particles right there. There are these Cr23C6, if it happens to be that, or Al220Cu-Mn3, or iron silicon inclusions also. In aluminum, it's very common to have iron and silicon containing inclusions, because iron and silicon comes as an impurity with aluminum. It just comes with it. Okay, so this is how, and you can measure the particle size after the fracture also. Yeah? Okay, I know you guys are getting hungry, so we'll get there. Let me skip this thing. We'll come back to later. Great piece of work. I copied it from Hosford and Cadell's book. I didn't do a good job. As you can see, it got cut off right there. One of the classic figures in aluminum metallurgy, just in metallurgy, ductility on the y-axis, volume fraction of inclusions on the x-axis. So as the volume fraction of inclusions increases, look at the beautiful curve. Look at all these different materials, copper, chromium, copper this, copper that, Nice piece of work. It was done back in 1955 or something, this work, or maybe 60s or something. Very nice graph. Systematic work. So here I put down some pictures for you. Layer 2024 aluminum alloy, here is the composition. Here are the second phase constituent particles, same thing. So here are the particles that you see. This you can see under an optical microscope. This picture you can get in an optical microscope. You can get it on a nickel-based superalloy also, Inconel 718. I will give you exact composition if you remind me later. Here, a picture of the chromium dispersoid under the transmission electron microscope. See, this is the twin boundaries in the particle, okay? Because the particle has got its own crystal structure. The aluminum has got its own crystal structure, FCC. This chromium-containing dispersoid has got its own crystal structure, its own lattice planes, its own slip planes, its own twin planes, and all that stuff. So you can see the twinning going on in the particle itself. And you can image that using transmission electron microscope, okay? So this is a good picture. Lutko and Lawlin. This is David Lawlin from Carnegie Mellon, He retired now. Okay. Okay. We'll come back to this later. I don't want to. This is a good place to stop if you want to stop. Or what time are we thinking? 1:30, right? What time do we supposed to go? 1 o'clock? Okay. So let me just make sure that I connect the whole picture of what we talked so far. Okay, let me skip this thing. So what I was talking about was all uniaxial tension, single axis. But remember, if I have a pressure vessel like this, if I have a pressure vessel containing some kind of a fluid in it under high pressure, I can actually calculate. I was trying to look for the damn equation, I couldn't find it. Do we have an eraser here? On the board. Oh, yeah. Oh, okay. So if you, what was I talking about? Huh? Pressure vessel. Thank you. So if I have the pressure vessel like this, okay? If there is a pressurized liquid in that, so this is my thickness. Oh, there is my thickness T, okay? And it's under pressure P. I have the radius of the, we have mechanical engineers here. You guys are mechanical, you know what I'm talking about, right? Yeah. So correct me if I go wrong. That's your job. So if I have the pressure, I can calculate the stress, right? What do I mean by that? I can have a circumferential stress like this, which will form a crack like that, right? Or I can have some other stress. But this is the stress that I'm interested in most of the time, because that's going to form a longitudinal crack, which is going to propagate along the direction, right? This equation, simple, right? Very powerful equation. Why? Once I calculate that sigma at which this crack will form, if you tell me what this material is, I will take let us say this material is 2124. I can look up the fracture toughness of this. We'll talk about fracture toughness later. I'm just throwing a little carrot in front of you. Okay? I can look up the fracture toughness of this material, K1C of this material. Which is a material property. Which I will talk about this later on. Tell you what the crack length would be when it fractures. Because K1C is equal to sigma times square root of pi A. We'll come to this later on. This is elementary fracture mechanics. We'll talk about this. But I just wanted to throw this at you before lunch. So if I know my fracture toughness, if I know the pressure of the contents inside the pressure vessel, I can calculate this C, and I can tell you what the crack length would be. How much would it be? So that I can constantly watch it so that it does not become a critical crack length before the whole thing bursts. So that's a very powerful. And pressure vessels are everywhere, okay? It's everywhere. Pressure vessels are everywhere, right? It's a very common thing. So that's that pressure vessel we're talking about, Okay? So this is a little bit of different type of a loading, right? It's not like doing a tension test. It's more like a hydrostatic type of a test, right? And of course, this is your bending, right? So if I take a ruler or something, and if I bend it, this won't bend. This is pretty hard. If I'll break it if I bend it too hard. So if I bend it like this, oh. If I bend it like this, the top surface is under tension, right? This top surface is under tension. The bottom surface is under compression, because it's like this, right? The bottom surface is under compression. The top surface is under compression. So if I'm doing a 3-point bend test, I'm going to erase this. You may have to write this down. I don't know if I have this in the notes anywhere, but I can put it back up again. But we'll talk about this again, I'm sure. Okay, so if I'm doing a 3-point bend test, which is a very common form of testing, okay, where I have a rectangular sample with a little bit of notch in it, obviously the way I'm going to load this is by putting forces like this, so that I bend it like this, right? This is coming down and I bend it like this. So the crack will propagate. I'm representing the crack by this wiggly line. Right? Okay, so that was the stress distribution under bending with no stress concentration. Of course, I put a stress concentration there by putting a notch. But even if you didn't have that notch, you still will have the same phenomena, right? Even if you didn't have a notch, same thing. And we'll talk about this in just a second. Well, actually, that second is right now. So, extremely important concept. Very important concept. Why? Because in every structure that we have out there, you always have some kind of a notch. Whether that notch has been put because of bad machining or some other reason. Of course, I'm making it look very big, but remember, when it's there, it's probably just a little scratch on the surface. And if you're applying a load here, so if there is no notch, all the load lines are pretty much uniform loading, right? Pretty much uniform loading. But once I put a notch here, I'm not drawing a very good figure, but you get the point. There's a more concentration of stress lines right there. Higher concentration of stress lines right there. So if my stress is sigma applied, if I'm applying a stress sigma right at this notch tip, because there are more stress lines there, so my sigma notch is equal, right? So if I have this notch, let me say the depth of this notch is A, from the surface is A millimeter. And the radius of curvature is rho, okay? Some kind of radius of curvature. My sigma notch here is equal to 2 times square root of A divided by rho. Oh my goodness, I don't know if it's the right formula. But anyways, I'm going to put it as a function. It's a function of this. It's a function of A over square root of rho. That's the important thing. Whenever I don't know exact formula, I put as a function. That way you can't tell me, hey, I put a wrong formula there. I just tell you it's a function. It's a function of something like that, yeah, 2 times A over square root of rho. In the afternoon. Keyhole notch. This but still more than this. Is K sub T. That's what the symbol that they use. Stress concentration factor is written as K sub T. And remember that, I'll tell you why it kind of throws people off. I'll tell you later on, okay? That's the stress concentration factor. But physics-wise, all it is just gets amplified, it just gets amplified. So K sub T is nothing but, let me write it there so you can all see it. Otherwise, only the front people will see. That will be discrimination. So let's put it. K sub T is equal to the stress at the notch tip divided by applied stress. Okay? That's this K sub T. Again, another thing in the literature, they will say sigma applied, they will say sigma sub 0, they will say remote stress. They will also say far field stress. It all means the same thing. They all mean the same thing. So basically, that's what stress concentration factor is, right? But keep that in mind. There's another symbol which looks like that very much. Okay, so we talked about tensile. What happened to my pointer? Okay, well, I'm losing my mind. Huh? Oh, yeah, here it is, okay. My jet lag is killing me today. Either that or I'm going crazy, one of the two. Okay, so here is your uniaxial tension, right? Here is your uniaxial tension, just along one axis. If you have a torsional situation, so basically the lines of force, there's more plastic flow. These lines essentially showing plastic flow. Brittle, don't worry about all this. I don't believe all this stuff. There is your compression. So basically tension, torsion, compression. Okay. Let's. So if you were doing, I don't know if you guys come across this, Raghav and you guys come across this, I don't know, press fit shafts? Okay. Oh, yeah, okay. Yeah. We'll talk more about this, the initiation, failure initiation, crack initiation. Is everybody okay so far? I'm not asking how everybody is doing. Is everybody okay so far? You can hear me, right? Yeah. Same thing, here okay? Yeah, okay. Thank you. So we talked about, yeah, please.
Ductile fracture.
Huh?
Case of ductile fracture,
Yeah,
we have brittle particle infiltration
right.
and a ductile matrix.
Yeah.
When you load this specimen, the ductile particle is not cooperating with the particle. That is the creation of void. The voids get squares. That is why the link formation takes place. Ultimately, it reaches a point from space. Cohesion takes place. But if you look at the direction, it is going to be almost 40-degree angle.
Yeah.
That is what the maximum saves direction. But how come in case of multiple phase system? Yes, you told about it is going to be only 40-degree angle. The 40-degree angle is the maximum saves direction. But in case of multiple phase, we are told about the cross.
Cross slip, yeah.
But that is not going to be again 40-degree.
Not necessarily, yeah.
But what 40-degree is not the maximum saves direction.
Right, right.
How come it is possible? Because the failure is going to be in case of ductile material only 40-degree.
Not necessarily. Not necessarily.
Because it's in case of ductile, it fails by shear.
Right,
But
absolutely.
maximum shear stress is developing only what?
Okay, you're talking about maximum critical result shear stress, yeah.
Shear stress.
Yeah.
It's only at 40-degree.
Yeah,
But only one direction is supposed to be there. But in case of multiple phase, it is going to be different direction.
absolutely. Yeah.
How is it possible?
Because you can have different angles of that cos phi and cos lambda. Right? See, that critical result shear stress is only for that particular plane. That plane, you got multiple planes in a crystal, right? We all agree that FCC has got 111. So I agree that in 111 plane, unless you reach the critical result shear stress on that plane, it won't yield, right? But if you have other slip systems, then you have to take them also into account. That's a very good question. Again, another processing question. That's what happens when we process materials, for rolling, for instance.
Because only one plane will have the maximum shear.
Yes.
We will not have that.
Right.
Two or three different. But the failure has to be only in the maximum shear stress.
Yeah,
But
okay.
how it is possible in two different directions?
Yeah.
And one more thing, in case of brittle fracture,
Yeah.
we have the same impurities. N number of impurities are present, but it fails by principal stress direction. Not going. Why it is? In case of brittle fracture,
Yeah.
you showed about there's no neck formation. Necking
No,
is
there's
not-
no, yeah.
So that is the direction of the principal stress.
Yeah.
It's not the shear stress.
It's a normal, yeah,
Why?
Normal
Same-
stress.
Same process that there also happens.
yeah,
There also you have particle impurities.
right.
Brittle particle.
No, but there are no impurities there. We're not talking about impurities when it comes to brittle fracture. Because there, the crack formation is all due to normal stresses. No shear stress playing a role there. That's why, right?
There won't be any shear stress.
Yeah. No shear stress playing a role there. It's all normal stresses. Sigma, not the tau. Yeah,
That's what that different planes of shear.
absolutely.
That is what
Absolutely.
the question is.
That's why you had to,
But only one plane is supposed to be there. Only one plane will have the maximum shear stress.
yeah.
But in case of multiple phases, how come it?
But see, after that plane has yielded, you got other planes coming into play also, right? You just cannot consider just one plane all the time. You got multiple slip systems, right? It's a very popular problem, actually, what you're asking.
That means principal keeps on varying.
Of course, it has to. It's only for that particular situation, whatever you're saying, right? Yeah. I'll bring you're raising good question, actually. Let me see if I can find a problem on that. Yeah. That's a very popular problem in the mechanical metallurgy.
Planes will not have different shear stress.
Huh?
Maximum stress.
Right.
We talk about the multiple phases.
Yeah, absolutely. Yeah. Actually, let me go there directly. Maybe I have that slide that you're talking about. Just 1 second. So this is what you're talking about essentially. Yeah. So basically your stress axis is that way, and you got your slip plane, slip direction. Your shear stress is cos phi, cos lambda, right? So I just put in some numbers there, and I got sigma equals to 45 MPa. So the question is, will the single crystal yield in this situation? It will not yield because it's only 18.4 MPa when you do the calculations. Because it has not reached the 45. Okay? But we'll talk more about that. I think you got a point there. Okay, so we'll talk just a little bit about, so like what we said was body-centered cubic materials, okay, BCC materials like iron, steel, titanium, beta titanium, and other materials, they have a ductile to brittle transition temperature. So let me get my thing here. Yeah.
It will be at lower temperature or higher temperature, time to brittle? And temperature will be
Decreasing, yeah. That's a good point, actually. So let me show you the next slide, and then we'll come back here. Okay, so since you asked that question, so influence of temperature, right? And this is the energy absorbed on the y-axis, temperature on the x-axis. So what I do is, it's a very simple test, actually. So I take one of these Sharpie samples. Okay, it's like a 3-point bend. So there is your, I drew here the picture before. So you bring this arm and you hit this sample right there. You hit this sample and it will fracture, right? It will fracture. And then you can record your energy, how much energy is absorbed from the scale, right? And then you plot that energy versus temperature. So a lot of times what you can do is you can use boiling water, 100 degrees Celsius, room temperature, 22, 24, whatever the temperature is. And then you can go to ice, 0 degrees Celsius. And then you can go to dry ice, solid carbon dioxide, which is available most of the time. I don't know exactly what temperature it is, I forget. Minus 40, right? Yeah, minus 40 degrees Celsius. Then you can go to liquid nitrogen. I know in degrees, minus 196 Celsius, right? And then you can go to liquid helium also, 4 degrees Kelvin. Okay, liquid helium is little bit difficult to get. But liquid nitrogen you can get very easily from the physics department, usually. All you need is just a little bit of liquid nitrogen in a little dewar, put your sample there for 5 minutes, take it out, and put it there, put it right there. So you can at least get 5 different temperatures without any problem, okay? And then you record your impact energies. What will happen is that in the case of body-centered cubic materials, most often you get a curve like this, very well defined, like a S curve, very well defined S curve. So right here where the inflection point, so inflection point where the curvature changes, here the curvature is up, here the curvature is down like this. So inflection point is right there. There's one guy missing. Where is he? You changed places, huh? Okay. Yeah, you were sitting there, you moved there and that. Where is that guy? Oh, I see. Okay. Okay, anybody, I just noticed that. Okay, so you get this inflection point. So that is your ductile to brittle transition temperature. Okay? That means above this temperature, the material acts ductile. Okay? And below this is your brittle fashion. It turns into brittle. It's a very important, actually, it's very cheap to do. Machining the samples is not that expensive. You can get a very quick ductile to brittle transition temperature, right? And the reason I like this is because, well, I don't have a picture of it. Okay. The reason I like this is because back in 40s, World War II, these Liberty ships, how many are you familiar with this accident? Okay, about 3 or 4 people. These ships broke into half. Literally, this is a crack. It was made of high-strength steel. These ships were stationed in Arctic Ocean, northern Europe. The day this guy failed like this, the temperature was almost like a little bit about 2 degrees Celsius or something, just above the freezing point of ice. But still, oh, you're sitting over there. Okay. Just 2 degrees Celsius, it broke into 2 halves because the ductile to brittle transition temperature was way high. During those times, the steel was not that good. So the steel during that time had a very high ductile to brittle transition temperature. So if I take a modern steel that is made today, where do you think the curve is going to be? The curve is going to be more to the left. Today's steel is going to be more towards the left so that it can operate at lower temperatures without getting into the brittle mode. Okay? So the new steels are like this. Also the Titanic, even in the case of Titanic, when they did the case study for the Titanic, those bolts were made up of steel bolts, steel rivets, and they also had very high ductile to brittle transition temperature. That's where the cracking started actually, when they started to do the analysis on that. Okay? But in the modern steels, it's more this way. And you will notice that in the case of face-centered cubic materials, there is no ductile to brittle transition temperature. It's all pretty straight curve. And we can prove all this using dislocation mechanisms, Cottrell's theory. We can talk about that later on. But I just want to show you some of these things. Okay, let's go to the next one. Oh, I can do it here. So the ductile fracture is more transgranular fracture. So the brittle fracture that we just talked about, cleavage, this is a brittle fracture mode, cleavage. This is scanning electron microscope picture. But you see, it's a transgranular fracture. Even though it is a low energy fracture, it's a transgranular fracture. It means the crack is propagating in between the grains and not along the grain boundaries. Okay? So this is a intergranular fracture which is propagating along the grain boundaries. Right? And when you look in the scanning electron micrograph, you can really see the grain boundaries right there. These are all grain boundaries. You can see the 3-dimensionality of the grains, right? But here it's very distinct. They both are low energy fractures. I want you to keep that in mind. They both are low energy fractures, but one is a transgranular fracture, one is an intergranular fracture. This is the cleavage, this is the grain boundary cracking, right? And so when you look at the cleavage, this transgranular fracture under optical microscope, this is the way it's going to look like, right? When you look under the scanning electron microscope, of course, you can have this, it looks like this as well, or you can have a very distinct riverline patterns. Very distinct riverline patterns. You see this? These rivers, river tributaries essentially, right? And again, it can look like this. In some materials, it can look like this. But in the case of iron silicon alloys, iron nickel alloys, they all show very good pictures like this. Okay, even titanium will show beta titanium. I worked on that personally, so I can tell you that's the way they look like. And you can measure these heights of these rivers, of these river heights, and you can put a dislocation theory to the whole thing, which I did with my advisor a long time ago. Okay. Oh, yeah. So you will encounter this intergranular type of a fracture. What this means essentially is that somehow the grain boundaries have gotten weakened. That's why it prefers this fracture mode, because the cohesive energy between the boundaries, it it has reduced, so they open up more easily. Have you ever taken mica sheets? If you take mica sheets, if you put a drop of water, they will separate more easy. The drop of water will decrease the cohesive energy between those mica sheets. We used to play with that when I was in college, I remember. You can separate the sheets out real easy because you're reducing the cohesive energy. So why am I saying that? Many times what will happen is there are impurities that will come and reside right at the grain boundaries, and they will reduce the cohesive energy at the grain boundary, providing the energy to fracture, which is much lower than any other type of fracture. A good example is in the case of aluminum lithium alloys. Lithium comes with some impurity like potassium and sodium. So they all belong to the same group, lithium, sodium, potassium. So whenever you have lithium, sodium and potassium also comes with that. So the Australian groups have shown that the sodium and potassium, they come and sit along these grain boundaries, and that is why aluminum lithium alloys fail by intergranular fracture at low temperatures. Okay? Because sodium and potassium can be liquid at room temperature, a little bit, liquidity. But when you freeze the temperature, or when you go down in temperature, they'll become solid and they will reside at the grain boundaries, leading to lower fracture. That's what the Australians proposed, which is not completely true, but they have shown that it works. That's why I mentioned that. Okay. So you come across the intergranular fracture, the one situation that I just mentioned. The other situation that you come across is in creep, high temperature creep. At very high temperatures, when you're doing a creep, when a structure is undergoing creep loading, like if you take pipelines, for instance, right behind this wall above this thing, I'm sure there are pipelines that are carrying water, hot water, to the bathrooms and all that, right? So if you can imagine for a second, instead of the hot water, if you have superheated steam, for instance, going through those pipes, you can have creep because the superheated steam will have a very high temperature. Then you got loads because there are hangers. The pipe are hung between, there are hangers between every so much distance, right? So if it gets too hot, for instance, the pipe will start to sag because of the temperature. That means it's creeping. So it happens very commonly in the chemical plants. One of the most common failures in chemical plants is intergranular fracture by creep. It's a common fracture mechanism in creep. High temperature intergranular cracking. Okay. Nickel alloy failed under liquid mercury, for instance. This is what I was talking about. Like, for instance, mica crystals with water. The same way nickel can fail if you put it in liquid mercury, it'll fracture by intergranular fracture really easy. Okay? Very easily. Intergranular fracture in high strength steel. Okay. Let me just do something. Just to put in relevance.
Suppose we increase the temperature of the metal. Suppose we increase the temperature of the metal, and there will be failure due to creep. But if the temperature is decreased, will it be more hardened or it will remain the same? It is not failed, temperature increased, and then it is decreased.
Yeah. So creep is a permanent deformation, just like plastic deformation. Hold your thought, 1 second. Just hold your thought, 1 second, right there. So for instance, to answer your question, you remember in stress strain, you remember in the tensile test strain, if I go up till here to the elastic, if I remove the load, that's what you're asking, it'll come straight back down along the same line. But if I go into the permanent deformation, if I unload it, I'm not going to come back like this. I'm going to come back like this. This is not recoverable. It's gone. It's a plastic deformation, is permanent. The same way under creep strain versus time, right? So this is in an instant. So here I am, let us say, for instance, if I take out the load, so there is some load here, let us say 100 newtons, okay? If I take out that load, it's not going to come back like this. It's just going to maybe something like that, because that is permanent. Only here, if I just quickly bring it back, yeah, it's okay, but not once it's gone there. So that deformation, the pipelines, the pipes that are carrying the steam, once they become like this, so the pipe that was like this before, and now it is, oops, this is permanent. This bend is permanent. Okay, so okay. We could have left it there. So that, okay. So okay. Sorry, I'm just going to add some more to what you were saying. I just thought about something, and that is, so this is my, let's see, okay. So this is my temperature. This is my stress. Let me draw this and then I'll show you. I'm just going to draw something, some. Okay. Well, I don't know if I need to do this right now. So this is like a creep map. Creep map. So you're loading to some stress normalized by elastic modulus of that material. This is the temperature like this. So here, very low stress, very low stress, very high temperature. So if I'm operating around this range, if I have a creep loading, that's the intergranular fracture I'm going to get. Because all the diffusion is taking place along the grain boundaries. So yeah, just let me draw a couple more. So all my vacancies are moving along this, which are going to form this voids, creep voids. So that's the intergranular fracture. We'll talk about more of this afterwards. I just wanted to put this in there. But remember this, we will talk about this afterwards, okay? So this intergranular fracture, this intergranular creep fracture that you're seeing takes place when you're operating at very, very low stresses, very low stress, no dislocation movement, because there's not enough stress to move the dislocations. No, not enough stress. But the vacancies can diffuse because the temperature is high enough. Oops. The temperature is high enough, so the vacancies will move. Okay. So that's what I just want to introduce to you. Okay. We talked about that a little bit. So I just wanted to put this picture in. Why? Because I wanted to convey one information to you. Yes? Huh? Yeah. Well, let's hold that thought for a little bit longer. Yeah. Right now, I'm just going to introduce things. We'll talk about that. It's a very good question. Why only BCC materials exhibit ductile to brittle transition, not FCC materials? So HCP also exhibit ductile to brittle. I forgot to tell that. Yeah. So one of the things I wanted to convey to you is that, so these days, one of the things that is happening in the material science is we're collecting a lot of data. We're putting databases together now. You know, large database. You know, what do you call large data? Huh? Yeah. So we're putting all these databases together, because we're moving towards probabilistic. Actually, it was always there, but we never used it as material scientists. We always talked about margin of error, standard deviation. You have 50 samples, take the average, right, of the 50, look at the standard deviation, and then plot this Gaussian distribution. That's what we used to do. But now we are going a little bit farther than that. We're going a lot farther than that right now. We're applying Bayesian statistics and all that, okay? Maybe we'll lead that to some other GIAN lecture. So what I wanted to show you was this, that, So this is my applied stress, because even though your component is seeing stress, but there's always these fluctuations. It's never seeing a constant stress. So if you think your component is seeing 50 megapascals, it's probably seeing 50 plus minus 2, 50 plus minus 5, constantly changing over a period of time. So that's what this is indicating. And this is indicating the material's resistance to fracture. So when these two guys overlap, that's where the fracture probability is, essentially. Just a little cartoon, nothing major. I just want to find that as a topic to switch, you know. So this is a safety factor that we employ, the old way of doing things. This is the old way of doing things. Because the new way of doing things is more, what is the failure probability? We're not worried about safety factors anymore, but still we use, in some industry, we still use factor of safety. So let us take, for example, well, design limit means we do not push the limit. Okay. So safety factor, if you want to operate something with yield stress as your design. Yield stress is your design. So let us say 100 megapascals is your yield stress, and you want a safety factor of 2. That means you don't want your component to go above 100 divided by 2. 50 megapascals would be your working stress, operating stress. So a lot of times, you know, we call in the industry. So if you guys are all sitting like this, so here are the loads guys, here are the fracture mechanics guys, here are the life prediction guys, here there is some other group is sitting. So those guys are calculating the loads. They're not interested in anything else. Those are the loads. Let us say you're the materials guys. You'll say, okay, I have a material 4340 steel, that's the yield stress, and he's saying I want a safety factor 2. He gives it to you, and you say, okay, and here is the operating stress. He's going to tell you, and then you calculate your diameter from the safety factor, right? We just talked about 100 megapascals, safety factor 2, working stress is 50, right? So then you go back and use these numbers, right? And you come up with this diameter, okay? This is just a problem with 220,000 newtons. Don't worry about that so much. Basically, what you're doing is it's a simple thing, essentially. Let me not make things more confusing than what they are. Basically, it's sigma. So you got your 50 MPa, right? Pi d square, yeah. Okay, I knew something was not right. So if it tells you the force, then you can calculate your D based upon this 50 MPa, okay? Because the loads people always work with only stress, the forces. They don't work with stresses. It doesn't matter to them. They're mostly interested in what is the gauge thickness? What is the gauge thickness? What is the diameter? Those are the only things they're concerned about it. So when we were talking about saving the payload, or increasing the payload, that means you're constantly decreasing your diameter to the safest level possible so that you can put more payload. But you can meet the requirements. You can meet the requirement of that, in this case, 220,000 tons or newtons. yield stress of 310 MPa, okay, for this problem, okay? And you basically calculate your diameter. Everything is clear? So that's all what these guys do in the aircraft business. It's not that complicated. Of course, these are coupons. But when you get to real structure, you got to talk to somebody like the finite element guy sitting there in the back. He didn't hear me. Okay, so. Oh, I hate hardness measurements. We'll leave this to the end. I'm not too crazy. I'm not too interested in it. We'll talk about it. Now, okay. Everybody, how many people have done hardness test? All you friction stir welding guys do this hardness test, right? You friction stir weld something, you go from the weld zone to the heat affected zone and see how the hardness changes, right? So, yeah, okay. We don't have to talk much. Oh, this was what I was supposed to do before break time. Okay, so now I'm going to switch topics a little bit, okay? I'm going to go to more interesting things. We'll come back to this later. I got more slides here, actually. Yeah, we got more slides here. Let me get to the. What am I supposed to do? Okay, I know where it is. Sorry. Okay. Okay, so I'm going to just give you some basics of fracture mechanics. Okay, I would like to do this because this is a good time to introduce. I'm trying to see. Okay. Did anybody figure out what the stress concentration factor equation is exactly? Okay. So this is where the fracture mechanics began, right? So we talked about the Liberty ships. You know, President Roosevelt and all that stuff, 1942. They built 2,700 ships, okay? The ships broke apart due to low notch toughness of the steel, which was made worse by low temperatures and also residual stresses. That means there were tensile residual stresses, not compressive, okay? This led to the development of fracture mechanics. So when these shapes started to break into halves, then they said, okay, what is wrong with this whole design? What are we doing wrong? Okay, so this is when the fracture mechanics started, right? Because up until this point, we were still working with notches. The notch that we just described before. Let's see. So basically, we were talking about sigma applied. Number 2, we were talking about dBTT. Number 3, we were talking about yield stress, UTS. So these were the only concepts. This was the only concepts we knew before 1942. There was no fracture mechanics yet. We were dealing with notches, okay? So plasticity, mostly notch plasticity. That is K sub T is equal to sigma notch root divided by sigma applied. And this was a function of A over square root of A over rho. These were the things that we were using to design components, ships, whatever we were doing, right? So then we started to talk about the fracture mechanics after this. Let's see how, oh yeah, there is that formula I was struggling for. Sigma m is equal to 2 sigma sub 0 A over square root of A over rho. So we're pretty much very close to what we thought it was, okay? So the notch stress concentration factor is sigma sub m divided by sigma sub 0, which is the same thing there. Sigma sub 0 or sigma applied, same thing, okay? So this was the notches and state of stress ahead of a notch. This is what we had in the hand to work with. That was it. Okay. And this is just other things. Let me see where I am. Top. So elements of elastic deformation. So basically everything is elastic. No plasticity involved. So we're still talking about Young's modulus, stress divided by strain. Nothing more, nothing exotic, right? So you can see these normal stresses and shear normal stress, 1, 2, 3, or whatever notation you want to use, shear stresses, okay? And there is your hydrostatic stress, which is 1/3 of sigma 1 plus sigma 2 plus sigma 3, right? That is your hydrostatic stress. And we talked about this pressure vessel also. Sigma is equal to PR divided by 2T, right? So these are the kind of things we're dealing with, and so oh, it's me. Okay, touching that. Okay. We talked about this. Okay. Yep, you're good. Yep, you're good. Yeah, okay, good. Thank you. So here we are, just a few concepts here. Just a few concepts. So we talked about this, all these three things here. Okay. Then we are talking about the von Mises yield criteria. So this is the principal stresses sigma, sigma 1, sigma 2, sigma 3. Principal stresses. And this is the equivalent stress according to von Mises, square root of this, right? Okay. That's fine. You all know what edge dislocation is, an extra plane of atoms in the lattice. We talked about this. So everybody knows this Griffith's theory, right? Okay. So if not, when Griffith was doing his experiments on glass, basically, very simple, a lot of these questions, a lot of the discoveries come from simple things, like an apple falling and Newton says, aha, I found gravity. The same way, when Walt Griffith was my boss actually. Griffith, when he scratched the glass, he found that to be easy to break the glass, right? So you create two surfaces. Two surfaces have been created when you break the glass, right? One surface, the second surface. And each one has got a surface energy of gamma sub s, right? So this is the equation that he came up with, right? The critical fracture stress to break the glass is a function of the elastic modulus of the material, surface energy, and the crack length. The length of the scratch that you put in. Purely based on a number of experiments on fitting the data, critical fracture stress, fitting the data, I'll never get this right. Fitting the data between critical fracture stress and length of the, if you look at Griffith's paper, that's what you will find essentially. What is the critical fracture stress and what is the crack length that you put in? And basically that's the equation that he fitted the data to, okay? But this is the interesting thing. So the critical stress for brittle fracture according to Griffith is this equation we just talked about. Okay? Found the equation to be in agreement with crack in a brittle glass. So you take the square root of pi a to the left side. Sigma sub c square root of pi a is equal to square root of 2e gamma c, right? So Westergaard's solutions and area stress are on some trigonometric function here. This comes under advanced fracture mechanics. Okay. These solutions will come under advanced fracture mechanics. So George Irwin So after the Liberty ships started to crack into two halves, Irwin was working at the Naval Research Labs, and he was given the task of looking at what exactly happened. So he started to do literature search, and he came into this mathematical analysis in the plasticity theory, this guy Westergaard solutions and also area stress functions. When you go through those things, that was one of my PhD exam, oral exam question. You come up with this final equation, K is equal to 1 over square root of 2 pi r. So essentially, there is your coordinate system. Let us say r theta. Okay, some angle there. And the K value here. So this K is not the same K that we just talked about, the stress concentration factor. It has got nothing to do with that. That's what I want you to be careful about. This is totally different, this K. Okay? So there is a relationship that exists when you solve all these things. Stress intensity K is a function of 1 over square root of r times a trigonometric function. Sine and cosines, nothing more fancy than that. Okay? That's all. One more thing. Stress intensity. If you want to put this crack there, that is fine. So what I have a situation here is, a very sharp crack, not a notch, but very sharp. Actually, there's a very sharp crack here. I got a coordinate system in front of it. And I'm loading this crack in a tensile mode or a mode 1. I'm opening this crack. On the distance away from this crack tip, a very sharp crack tip, atomically sharp crack tip, that's the key. Atomically sharp crack tip, I can define a K value, a stress intensity value. It's got nothing to do with stresses and strains, nothing like tensile stresses and strains, but a totally different variable, K. I can define that K using this. And the conditions are that when I apply this load or this stress sigma to this crack tip, everything is elastic. Everything is elastic. There's no plasticity involved. Everything is elastic. No permanent deformation anywhere, including at the crack tip. So this is called as linear elastic fracture mechanics. So it is fracture mechanics, but elastic fracture mechanics, because the assumptions are all elasticity, pure elasticity. No plasticity involved. When plasticity becomes involved, we have to change everything around, which we can do that later on. When we go to high temperatures, when the material is much more plastic, okay? Or when we talk about soft materials, very ductile steels, we can talk about that. I mean, that will be more plastic. But when the materials are very brittle, very cold temperatures, very brittle materials would show flat fracture, no plasticity involved, not much dislocations involved, behaving elastically. This is the equation that it's supposed to follow. So this was not there before. These equations were there in the mechanics area. You know, these equations existed, but we never used them to materials. So Irwin was the guy who said, you know what, I'm finding something in the literature that I can relate this equation looks very interesting. Especially it started to look very interesting when Griffith got his results this way. So when Griffith said, hey, I'm getting some results on glass, which is very brittle, totally elastic. When I put a scratch, which has got a length A, and if I put a stress sigma, I get this equation. You know, you can plot this equation. And look at the similarities. They start to compare the similarities. Sigma times square root of pi A Sorry. Okay, sorry. So, oh, you want to make this correction. There is sigma here, there's K here, okay? Sigma times square root of 2 pi A. Sigma times square root of pi A. Sigma times square root of pi A. So that similarity was observed between this analysis and this analysis. So they combined the two and they defined. So this is the next step. So one can write K, forget about this C for a second. K is equal to 2E gamma sub C. So this K, 2 square root of 2 pi R, was taken and it was used here. Surface energy. Yeah. But there is no surface energy in those analyses. It is only Griffith's. So this is Griffith's analysis. Thank you for pointing that out. Can everybody see this? I know this thing is coming in between. So there is my Griffith analysis. And there is my, if I may say, Irwin is not is the analysis, but Irwin's whatever collection of thoughts. I don't know. Yeah, Irwin's contributions. So here you have the surface energy, which is not there here, right? But we do have a sigma square root of pi A. We do have a sigma square root of 2 pi R, okay? And there is no K here yet. There is a K here, and then there's no K there. So, but the similarities are there. Then they said, okay, let us relate K is equal to sigma times square root of pi A. Stress intensity. Not the stress concentration factor, but stress intensity is equal to applied stress times square root of pi times the crack length. And this crack length idea came from the scratches from Griffith's glass work, right? For different scratches. Something like that, right? This was the birth of fracture mechanics. All this happened during the 1960s. Early, 1960s. So in linear fracture mechanics, I had this equation here. In linear elastic fracture mechanics, the stress ahead of the crack tip is written as sigma YY is equal to K divided by sigma 2 pi R. And that actually is nothing but, this is your sigma YY. This is your Y direction. So if you take this point here, sigma YY, sigma XX, sigma ZZ. So you can define all the three stresses at any distance R from a crack tip in an elastic body. Okay? This solution, however, was for an infinite plate. Okay? I didn't write it down there. This solution is for an infinite plate. I mean, this is normally what we do in most mathematical solutions, right? We define for something for an infinite body, and then we bring in the boundary conditions afterwards. So this is a important, very important evolution in the whole fracture analysis. Before this, everything was designed based on yield stress, tensile stress, ductile-brittle transition temperature, and all that stuff. Okay? So let me see what the next slide is. then you see there is a, of course, we just talked about the Irwin modification of Griffith equation, which we just did. Okay, so plane stress, plane strain. Okay, hold your thoughts there for a second. Okay. I'm trying to see the best way to explain this. Because now what we're doing is we are bringing in the mechanics into the whole thing. And I don't want to make it too mechanics here. Okay? I don't want to be stumbling myself. Okay? I want to make it more simple, my own life, instead of making yours complicated and mine more complicated. Okay. So what we will do is this. I'm going to draw a couple of things here. Nothing. It's just eraser. Yeah. Just eraser. Professor Arora was worried, what is he breaking now? Okay, so this is what I'm going to do. Okay, let's do something like this. Okay, there is my crack. Okay. Okay, I'm going to draw two pictures. Can you see from there? Amit, can you see? Huh? Okay. And I'm going to draw a picture next to it. Well, let's make it the same length. Huh? Okay. So, okay, something like that. What's the difference between this and this? Okay, everything is same. First of all, what are the similarities, right? I'm going to define width of this specimen, okay, of this finite specimen instead of an infinite plate. So if you basically, if you take this and if you take all the way over here, that will become an infinite plate. But I'm going to bring this dimension over here and make it more finite. This is my thickness. From there to there is my thickness. B is my thickness. And luckily, this is what everybody uses in all fracture mechanics books. Thank God. Not everybody is not changing to something else. That is my B, thickness. And my W is defined from the center of the loading. This is my load line. My load line, right? And also this is mode 1 loading. Mode 1 loading is a very fancy term for tensile loading, tension. Because we have to sound sophisticated, so I'm going to make it mode 1 loading, okay? So it's basically a tension mode. Tension mode, there is a load line. My load line to my end of the specimen is my width. That's how I define the width of the specimen, there to there. Okay? Yeah. Yeah. You had a question, yeah. So I'm looking at the front face. Huh? W is my width. WID. Yeah, W is my width. Yeah? and B is the thickness. The reason I'm writing this thing down is if I just showed you the slide, you will never follow what I'm saying. But if you write it and then you can write it, start writing, then you'll see what I'm talking about. Huh? W is that width, yeah. Yeah, from the load line, from the center of the load line, right? From the center of the hole. In that hole, my loading pins go in. My loading pins so my pins go in there on the way to the back, and I put my pins to load it. So that's my load line, right? And from my load line to the width. So for example, can we lift this up for a second? Is there a button to push it up? Okay, I won't touch anything. Yeah, okay, that's what I was doing. Yeah. Oh, maybe it's going up. It's going up? Yeah, oh, yeah, slowly, okay. Slow but steady. Okay. Yeah, if you just want to put up the computer just for a second. We're not done yet, but just temporarily, if you want to. I just want to make sure they can see what I'm doing. Yeah. So this is the... So there is my... so things will become very simple. The only thing is the concept is a little bit hard, but once you have the equation, it's very simple actually. Unless you become a real fracture mechanics guy, then things could be tougher. Okay, but we are not going to that point of getting into the fracture mechanics totally. That will be dealing with integrals and all that. Okay, but for our purpose to relate materials behavior, we just need a few things. That's all. Just to have this for this lecture. Okay, but for advanced fracture mechanics, we have to dig into it. Okay, but we're not doing that. So, and the same thing here also. And I know I was going to show you something, W, and there is my width. There is my thickness, B. Okay? There's my crack length. And let us say my load is P. P is the load that I'm applying. That's the load I'm putting on the specimen so that this crack will propagate. Okay? The crack will propagate. And the way I define the crack length, so I need one more term. A is equal to crack length. So what we do in fracture mechanics is, because we are dealing with elastic fracture mechanics, we just cannot take a notch sample and do the test. We have to put a sharp crack in front of that notch. And many times what we do is we go to the fatigue machine. We go to the fatigue machine and then we put a fatigue crack, which is very sharp. Okay? And I'll show you how to do that afterwards. In the same analysis, I will go through a procedure verbally, and if we have machines downstairs, I can show you that also. Okay? I have to talk to Dr. Rora about that. Okay? So, because it is linear elastic fracture mechanics, because it is linear elastic fracture mechanics, we have to have a sharp crack in front of the notch tip. Let me write that down. We have to have Because if we don't have sharp crack tip in front of the notch, then we will end up with the notch stress concentration factor, right? If we don't have the sharp crack tip, we'll end up with the stress concentration factor, and we don't want that. We want linear elastic fracture mechanics. So we want to keep that tip very sharp. Okay? So once you do that, we just go back to this equation one more time. This is the solution for an infinite plate. Okay? Okay, for an infinite plate. So I'm going to put a 1 there. 1 refers to mode 1 loading. Which is tension loading. Uniaxial tension loading. We're not doing shear test. We're not doing a torsion test. Okay? Of course, we have to change the specimen design if we want to do that. When you're working in the laboratory, it's not easy to work with this. There's no way you can define the stress in this case, unless you do finite element analysis. Because when you had a round sample, for instance, or a square sample, you could define the stress. Because we knew that the stress was, I'm going to take a cylindrical sample. We knew that stress was equal to P divided, load divided by area cross section, right? Load divided by area. And we could define here the area was pi d squared by 4, whatever. Here, how are you going to define the area? It's not easy. Okay? So, even though this equation comes out this way because of these analysis, area stress function and Westergaard solutions and all that, the equation comes out to be this way mathematically, but realistically, when you want to really determine what the K value would be, you have to deal with the loads. That's why I said, here are the loads guys, here are the materials guys, here are the other guys. That's why I said that. Because when you go to the industry like Lockheed Martin or Boeing or any other place, aerospace industry, you always call them as the loads guys. That's how they're called as. So that group is called as the loads group because they deal with this load, not with the stresses, loads. Huh? Okay. So, fortunately, we can write this equation in terms of loads. We would not worry about what the solution is, how the solution came about. Let's take the solution for now. This is K is equal to P divided by B W raised to half F of AOW. So I'm going to put this as equation 1, equation 2. So just look at it for a second. I machined this sample in the laboratory to test, right? Are my Air Force guys listening in the back, or can you hear me? Yeah. So if I machine this specimen in the laboratory with a certain thickness, a certain width, a certain height, not important, but let's say a certain height, and I know the crack length, how much it is. The crack length is from here, from the load line to the tip of the crack tip. Well, actually, this should have been here, or this could have been here, but that's okay for now, okay? So everything is measured from the load line. But this is not totally accurate, what I've done, actually, I just noticed, okay? I mean, everything is okay, just a little bit here and there. So K is equal to load, which I know how much I'm going to put on the machine. I know that. It's very easy. I know my the thickness of the sample. I know the width of the sample, square root of W. The width of the sample I know. I know the crack length. And I know my W. And F of AOW I know because we have already done the calibration. I have this available to me. It's independent of material, purely geometrical. Lookup table. Okay? So I have that. So I have this for different geometries also. I can have a geometry a little bit different from that. I can have a geometry like this. I'm going to load it up like this. Okay. So same thing. I know the W. In this case, the definitions are a little bit different. W, A. I mean A from here to there. Okay. So for this geometry, this is a center crack plate. Okay. For this also. Center crack plate. I have same thing, AOW versus F of AOW. I have that table available. Okay. And I have this is called as the compact tension design. Sure. Yeah, you can same result. Very good point. Independent of specimen geometry. CT specimen. It's easy and more used to it. You like 3-point bend? I'll go and use 3-point bend. I don't like 3-point bend. I like compact tension. I'm used to it more. That's what I have used all my life. So, but 3-point bend is good. Yeah. 4-point bend is okay too. But 3-point bend, you like 3-point bend? Use 3-point bend. Yeah, absolutely. So you crack it in tension compression, right? You have to do it in, yeah, you have to fatigue it. No, compression maybe. You can't take the thing off, right? You have to just, yeah. That's what I don't like about it, maybe, yeah. We'll talk about that. I'm coming there. I just want to introduce that, yeah? So yeah, thank you for bringing that up. So like, you know, you can do it like this, like he said, 3-point bend. Excuse my drawing here. You're not taking a picture of this, are you? Okay, let me try. Okay, there is my 3-point bend. So it has got its own, lookup table. Okay. And so where am I going with all this? Actually, I started to say this something totally different, but I had to go through this. So here is my thick specimen compared to this. So let us say this is B1, B2, just for discussion's sake. In that compact tension specimen, so hold that for a second here. Okay. Should have a different pen here. Or let's use some colorful pens here. Okay. What I was going to say was, okay, yeah. So, yeah, let me go here. So that's my equation, right? That's my equation for the infinite plate. When I work with specific geometries, what I do is I just put a y in front of it. Where y represents the geometric correction factor. Huh? Oh, he was speaking. Geometric correction factor. Okay? So, more importantly, what I want to tell you was, so there is the notch and there is my crack tip. Okay? I'm just putting this wiggly line to represent crack tip. And I'm loading the specimen with a P. At some point, so I'm going to draw the curve the way it's going to look like. P versus crack opening displacement. So the load versus crack opening displacement. Okay, the way the crack is opening. Okay, or crack extension, whatever you like to do, doesn't matter. Whatever you want to put here. If you want to put crack length increment. Maybe that's easier for right now. Crack length increment. So the way so I'm monitoring it with some kind of a gauge. There is my gauge, LVDT. Here's my sample actually. Okay, geometric. Why am I rushing? I got 10 more days. I shouldn't be rushing. So the load is going up, the load is going up, load is going up. It's going to do this. So the specimen is able to sustain the load. There's no crack increment. This much crack increment is not a big deal. Nothing has happened yet. It's all elastic. So if I don't want to do the test, I can unload it. Nothing will happen. It will come right back along this. If I change my mind not to run the test. But I'm running the test, and suddenly, just a little bit. As soon as it jumps, you'll see a sign, the load will drop a little bit. Every time a crack jumps, it increases in length, the load falls, always. you want to. Maybe you don't want to call this. The first jump in the crack length critical load. Okay? Nobody wants to follow that. For many years, this is what we have used. Organization D, so we're all given the same material, same specimen design. We all go back to our laboratory. We all do the exactly same test. We write down the deviation in the temperature. Yours may be plus minus 3. His may be plus minus 2. Hers may be plus minus 4. So we all do these things and we come back together for discussion. What did you find? What was your experimental experience? Okay, I found a change in the temperature this much. My measurements are probably plus minus this much. It's called as round robin testing. So this is how this standard was developed. Round robin tests. It's called as round robin testing. When several organizations get together, and it's all volunteering work. Nobody's going to pay you for that. So you just take back and bring back the results, and we all discuss and develop, and we write the standard exactly what it should be, because we have first-hand experience, because we all have done our tests, right? So in that one, it clearly tells you how much is allowed, how much temperature variation. Yeah.
Here also we are having pi. It was for some round pi will become only when we are having.
I'm trying to think. Yeah, I'm trying to think why the pi is coming there. I know in the area stress function there is no pi. Oh, there is a pi there. Okay, there is a pi. Yeah. Maybe it's got to do with the polar coordinates. I don't know. Polar coordinates, maybe. Maybe the polar coordinates. Yeah. This guy, he probably knows the answer. Yeah.
What will happen to the temperature?
Pardon me?
When the temperature increases,
It's most likely it will increase. Again, it depends. Depends, right? So in some materials it goes up. In some materials it goes down. Yeah, yeah, yeah. And you have this extensometer. It's terrible when I look. That extensometer, actually, it's got these rods, quartz rods, which goes into the furnace opening. And your specimen is. So there is your furnace. So these quartz rods will go and sit there through the furnace opening. Yeah. And some people use back face strain gauges also. So these have become very common now. When I was doing my testing, it was not common. We had to build this in-house. We had to build it ourselves. They were not available at that time. But now everything is available. Yeah. Yeah. I mean, this has all become more common in last 20 years ago. MTS, 20, 25 years, yeah.
They're trying to get the K1C value. Because of the specimen they get the invalid, we cannot call it as a valid K1C. Is that input of that KP value?
That's where I'm trying to go. I have not been able to get there. Yeah, I'm coming there. Thank you for reminding me. Yes. I'm still trying to get there. Why do I do this? Yes, thank you. So anyways, yeah, so that's where we are, right? So that question is the right, appropriate question. So here is my thick sample, here is my thin sample. So this is what I'm going to do. I can explain things better this way, okay? If I plotted what you just said, fracture toughness, but I'm not going to call it as K1C or K sub C. Let me call it as K sub Q, okay? So K sub Q is my fracture toughness. So did I define the fracture toughness? Probably not. So when this crack length became critical, my K becomes critical. That critical K is my fracture toughness, okay? When A becomes critical, when A becomes critical, my K becomes critical, but I'm going to call it as K sub Q for now, okay? It's become critical, but I'm going to call it as K sub Q. It has become critical because my A is critical, so this is critical. That's the only guy that needs to be, right? But I'm not going to define exactly what it is. I'm going to do that now, okay? So if I plot my fracture toughness as a function of thickness, when the specimen is very thin, so if I have like aluminum foil, for instance, very thin foil, or take the aircraft fuselage is about 0.3 millimeters thick. Okay? Actually, even less, maybe. Sheet. It's a thin sheet. But remember, we're putting. So you got one sheet, you got another sheet. You bolt this sheet to this sheet. Okay? And then you got another sheet. So you got 1, 2, 3 layers. That's why it looks thicker. But they're sheets, basically. Very thin sheets. So if I start from a very thin sheet, let me not put a 0 here, because I'm going to run into a problem maybe if I put a 0. What is the definition of K? Let me start a very small number. That's the way the curve is going to look like. So what that means is, after I reach a certain thickness, my K sub Q will not change anymore. That is my plane strain fracture toughness. It's a poor man's way of defining, but I'm going to act poor man for now, okay? So to answer his question, he was just asking a question along these lines. So if I have a sufficiently thick material available for me, out of which I can machine a sufficiently thick specimen, I may be able to get this plane strain fracture toughness because it is thick enough. But what does it mean in terms of numbers, right? What this is to meet this criteria of K1C, my thickness has to be greater than or equal to, I got to check this equation again. Sigma square ys. I think it's 0.5 here. Right? 0.5? Okay. So when I get this K sub Q number from here, and I divide that by the yield stress of that material, okay? I divide that by the yield stress of that material and I square it and I multiply that by half. The thickness has to be greater than that. If it is, then I have met the plane strain conditions. Okay? And normally what happens, why did I say it's a poor man's definition? Is because I'm not talking in terms of stresses and strains. In terms of stresses and strains, what plane strain conditions really mean is that because it's a thick specimen, right? So I have sigma 1, I have sigma 2, I have sigma 3, okay, right? And I have U displacement. Let me put this as X. It may be easier. So I have all the three stresses present. Am I right? In plane strain conditions. Huh? My displacements are only two. I only have displacements. There is no displacement in the z direction. Make sense? So I have all the three stresses present, x, y, and z. Okay? But I only have displacements in x and y, or x and y, but no z displacement. Okay? Or am I the wrong? Okay? If you go to plane stress now, they're all present. So that's the उल्टा हो गया है ना? है ना? I'm just look easy, okay? Are you? Yeah. Yeah. Those are the, I can tell these are the fracture guys sitting there. Yeah. So, so if I'm testing is, so your question is, what do I do, right? So you can either go this way, or you can go the R curve method to answer your question. So, I got to drink some water here. I get too excited when I talk. I can't. So, if I'm doing my R curve, so in the case of the big fuselage, if you take the 787 aircraft fuselage, it's so big. I mean, you can do small coupons like this, but the Boeing guys really used to, Airbus and Boeing, they like to do the big sheets, you know, in testing. But still, it's a thin sheet. So they will basically do the same test, but it's called as an R curve test. They'll keep on seeing how much load it can take. And when it starts to show this first sign, they can define this one, and if it goes on further, they can define these R curves at different points. The K is at different values. I mean, That's one way to think about it. Easy way to think about it. So you take the big sheet. Again, big means, I don't know, you have to talk to the industry how big they want to use. Airbus or Boeing, you can ask them. And I used to have those numbers with me. I'm not able to recall the numbers right now. But if you look at NATO AGARD has meetings. They meet every so often. They're usually about this thick books. All these guys come and discuss, just like we're discussing. In one of the volumes, they do mention the numbers actually for the R curve, exactly what they are. So you can usually find it in the library. I have one in my computer, but that's corrosion, I think. I don't think it's fracture mechanics. I can put it on the server. If Dr. Arora's server, you can ask him. Okay. So where are we right now? Yeah, so, but this is a typical curve. That's probably John Knott. I think he was the first guy to put this curve together, for different. I don't know how the thin film guys do their fracture toughness testing. The thin film, like when you're growing thin films, very, very thin films, few angstroms thick. And if you're interested in fracture mechanics, fracture toughness, I don't know what kind of tests do they do, but maybe there's a small loading machine and all that stuff. I have not looked into it, but but for us, big structures, this is the best way to go. Best way to go. This is the curve that you'll typically see. Yeah.
Is the
Yield stress? I don't think so. Maybe for ceramics, not for metals. For ceramics, yes, definitely. They do all the Weibull statistics that they do for ceramics because of the yield stress. For fatigue, it can make a difference. Yeah. Bigger the sample size or diameter, you have more. The probability of fracturing is higher. So usually you'll get a smaller number. Yeah. For fatigue, it will make a difference. But for yield stress, probably not. Yeah. Yeah. So this is basically, this is the fracture toughness. Yeah. Huh. You're getting what? Yeah.
The use of the PQ value, when you substitute the PQ in the equation number 2, you get the K1C.
Yeah.
The equation,
Yes.
it is possible to get the K1C.
Yes.
So that time,
Or K sub Q. Yeah.
that is a material property
Yeah.
for a given flaw size. For geometry and loading condition.
Yeah.
But in less than that, in case of plain stress condition, that becomes invalid.
It's not invalid, but you're right. It's not. Yeah. It's invalid or
Since
yeah.
condition, how you are going to evaluate the parameter?
Huh?
Plain stress condition. How to evaluate the K1C?
It just depends on the application. Yeah. Because like you said, it's not so much it's invalid. It's a dependence of thickness. It still is valid. It's called as K sub C. I forgot to mention that. Plane strain is K1C. Plane stress is Kc, right? So that Kc will keep changing depending on the thickness of the material.
Is it not possible to experiment in determine the
Yeah, you can. Possibly, yeah.
so from the E39 and same result?
Yes, you can. Yes, yeah. But you're always, sure, yeah.
No, but that is dealing with only plain strain fracture.
Right.
E399. But KC cannot be determined.
Well, again, it depends on the thickness. When you say it cannot be determined, huh?
There are less. It will be plane stress conditions.
Yeah, it will be plane stress, yeah.
That time it is invalid.
Yes, yeah, absolutely. It's not invalid. It's not, maybe the right, I'm trying to see the right word for it. It's not useless totally.
That is
It's,
not useless.
you're being too critical, which is okay. Which like, I understand. But it's not too invalid sometimes. It only means that you have to take a bigger thickness, a higher thickness. It's very common actually what you're saying. In aluminum alloys, it's very common that you will not meet the plane strain conditions. Guaranteed. Okay?
So it is not
Because you have to have a specimen thickness of 5 centimeters maybe. That will require a large load to do the test. And your load cell may not be adequate enough to do the test. Right? So you just live with that case of Q. You just have to live with it. Because your laboratory may not be capable to test anything thicker than that. So your test is still valid, but it's not meeting the criteria to define plane strain. But it may be close enough. Huh? Yeah, yeah. Right. So if your yield stress is low, your case of Q will be high. No, your B will be high. That too. Oh, can you see from there, all these things? What I'm writing, you can see from there? Oh, okay. I couldn't. Okay. So if this is high, this is low. If this is low, this is high. So if you have a low yield stress material, it's very tough to meet the plane strain condition, right? Yeah. So if you're testing high strength materials, it's much easier to meet the plane strain condition. So yes, you're right in a sense that it's not meeting the criteria. I won't be so harsh like you are being. You're right, it's invalid, but I hate to say it's invalid. It's not meeting the criteria. So what I will do in that case is to go to the J integral. So this is the K integral. That's why I said it's linear elastic fracture mechanics. Yeah. Yeah. Oh, you may not go all the way here. You may be somewhere over here. Maybe you're here somewhere. You may not go here all the way unless you're talking about very thin. Very thin. Then, of course, the testing even becomes more tricky because it's not easy to hold a thin sheet in a testing machine. You have to put some reinforcements. Then you have to go to J. Yeah, you can go to J1C. Well, you may be able to get J1C. Because what will happen is, this is not meeting the criteria, right? Let's go back a little bit. This is not meeting the criteria. So that means my material is a little bit too soft, right? More ductile, low yield stress. So there is more plasticity coming up. It's not totally linear elastic. So I will have to resolve to J. So I will calculate J, and then I will calculate K by using this formula. So I'll evaluate J1C, and then I will say, okay, let me use this formula. This formula is basically K square is equal to EJ. I will calculate K from there, but by basically dividing it by modulus. I will show you an example of this if we have time. In aluminum lithium alloys, of all alloys, I was surprised to see the authors use J1C because aluminum lithium alloys don't require, elastic plastic analysis, but they did use J. But you can quarrel with them because this guy's a big hotshot in fracture. So it's okay. I'm not going to tell you the name. I'm pretty sure you know the name. Yeah, but yeah, he's a big shot in the fracture mechanics area. So it's tough to argue, but I think it's okay.
For aluminum alloy, it's not possible because there will be a lot of problems zone ahead of the crack tip. So that time the K1 is not going to be very.
Okay. Okay, this is the time to introduce a new concept. Just a little bit. How are you doing on time, Professor? We have what? What time is it now? Oh, my watch is screwed up. Okay. It's 4:15. Oh, he's a slave driver. Okay. Okay. He's going to make me work for my money here. No, I'm just kidding. We can stay here all night, no problem. We'll take off tomorrow. Tomorrow will be off day. Okay. So everybody understands the question, right? So it's a very valid question, actually. So if we do not have in the laboratory, you're trying to determine K1C, and you do not have sufficient thickness to meet the plane strain conditions, what do you do then? In a way, that's the question. Because your analysis is not going to be valid, because it's not meeting this criteria. This very important criteria is not being met. It's not being met. So what do? We just take whatever thickness is available, and then we do a J integral test, because J analysis is elastic plastic analysis. It's applicable when your material is a little bit soft, or soft is again a bad word. It's a no-no. It's much more ductile, low yield stress material, right? Yeah, low yield stress material, ductile material. So you may even break down the linear elastic fracture mechanics criteria, right? So, but before we go to J, I want to introduce something. It's probably a good time, right? I didn't expect to go into this, but we'll go there because you brought it up. I don't have these slides. I don't think I have these slides that I've talked about maybe a little bit, but this one we may not have. So this is what happened. So this crack tip that we are doing. So this is how my curve looks like, right? Because what did we write there? Sigma yy is equal to k divided by square root of 2 pi r, right? Right? It's divided by. And then a function, some trigonometric function. So this is the graph, K, sigma and R variation, right? Square root of R. So what happens is this. If you look at this equation, when R goes to 0, you get very close to the crack tip, this guy blows up. It blows up, infinity. That cannot happen in practical terms. So what Irwin, there was another guy, I forget, I think it's R1. Anyways, what they do is they cut it off at a certain point. So they go very close to R, but not to 0. And they say, okay, we have gone up until there. Let me just make this curve a little bit like this. And then they cut it off, make it like this flat there. Because if they don't, this will keep on going, which is not practically possible. If R goes to 0, sigma yy will go to infinity, and that's impossible. It has to be cut off somewhere. So what they decided to do is cut it off 2 sigma ys, 2 times, 3 times yield stress. They cut it off. So, okay, so now what has happened, even though you're talking about linear elastic fracture mechanics, you're saying that the material is yielded. 2 times the yield stress. Material is yielded. There is dislocation movement. There is plasticity in front of the crack tip. So even though you're talking about linear elastic fracture mechanics, because of this singularity that you have in this equation, you're trying to cut it off, but you're trying to cut it off in such a way that you're assuming at least 2 to 3 times the yield stress has been met. Which means the interpretation of that obviously is you have a small plastic zone in front of the crack tip. It may be very small, but it is there. It may be very small compared to the width of the plate. If the width of the plate is maybe 2 inches, this may be a few microns. So it's small. God, I can't remember equations. So this plastic zone, R sub P, is something like this, with a 1 over 2 pi maybe or something, 1 over pi or 1 over 2 pi. So let us say I take, somebody's got a calculator? Who's got a calculator? Or who can do the Indian mathematics in the brain? You know, we're all known for doing our mathematics in the brain. You know, when the US Air guy, the CEO of US Air was an Indian guy, right? For quite some time. And all the people will say, you know, this guy can calculate all the numbers in his head. The CEO, he was an Indian guy. I said, that's nothing new for Indians. We Indians are all like that. You know, they can all calculate the numbers in their head without calculators, right? Most of us can. I don't know why, but we can. So 1 or 2 pi. So let's take the aluminum case. So let us say I give it 35. 40 maybe. 40, huh? Let us say 500. So 4 divided by 50. I have to take that back. I can't calculate this in my head. So that's in meters. So 4 divided by 50, 1.03? 1.02 times 10 to the minus 3. This whole thing? Okay. Meters. Okay? Okay, it's a little bit high. So that's what, 1 millimeter? Right? That's about a millimeter. So this plastic zone, if I take these numbers, which are just about, you know, right maybe, 40 MPa square root meters, okay, for the K, yield stress about 500 for aluminum, 1 over 2 pi, 1 millimeter. So this is 1 millimeter, and this is probably 50 millimeters, 2 inches. This is 1 millimeter. So I think, so in a way, you're still meeting linear elastic fracture mechanics. I mean, you're on the border, right? I mean, the material is yielded. It has gone beyond elasticity, obviously, but it's small. I think this will come out to be small, actually. If I take the right numbers, I think this will be more like few, you know, less than that little bit. But the point is, it does not meet the thickness criteria, so we'll have to go to J. So, no.
You cannot be quite with this criteria. Say, my actual thickness of the
Okay. And it falls in the
Yeah.
I use this plane strain condition value of K, I may end up with a very conservative design calculation.
Okay.
And I say sheet could be oversized.
Yeah.
Very much oversized.
Yeah.
And higher value of KC for things.
Yeah. Exactly.
So for plane stress problem, really problem with the plane stress problem, actually I have to use the actual K1C, whichever is for that.
You got a good point, actually. That's an interesting point. Yeah. So you'll be having a conservative design. Yeah. But the thing is, only thing we have to be careful is this. I know what you're talking about. It's a good thing to think about. But the only thing is you may be over-designing it. That's only the worry, right? Because you're trying to reduce the weight of the structure. So by taking that, maybe you're over-designing it because you're doing conservative. Yeah. Yeah.
Plane strain condition K is only just to establish the K as a property because it doesn't change afterwards.
Right.
So
Yeah.
actually changing that is not a property. Say that we have to make the plane strain in real scenario.
Yeah.
We may have to go for the actual K1C, which is for that particular property. Then only correct.
Yeah. Yeah. That's a good point, actually. Very good point. Yeah. Yeah. So what we are saying essentially is we will never go below that. Yeah. We will never go below that number anyways. So in that sense, you're being conservative by using that number. But I think you're speaking more from a technical point of view, right? I mean, I think the question is from still valid question because from a technical point of view, what is the right way to go about? I think the only way to go about is doing the J1C because that's what happens for many steels, especially that they use in the power industry. That's what happens a lot of times. Most of the power industry fracture toughness values are J. That's why J actually came about because K was not working out perfectly for them. Then John Landis, I know John, he did most of the work. He headed the J integral, yeah. Yeah. So does everybody is okay with so far what we have done? So the basic thing I want to remember is, so the stress concentration factor is totally different from this. Stress concentration factor comes because we have either holes. So I'll tell you, for instance, a good example would be, I want to erase some of this stuff. We don't need it anymore. At least this part. So in the aircraft construction, I mean, do we have a device here? If I put a textbook or oh, do you have that thing? If you put a textbook, it will project, right? If I have a paper on this one. I'll see if I can look up this lookup table in one of the textbooks that I brought tomorrow. Yeah. What was I going to say? Huh? Oh, yeah, yeah. So that's my fuselage skin, for example, right? So I have my other fuselage skin underneath this. Okay. So there is my other fuselage skin. So these are overlapping here. So these are joined by rivets, right? These are joined by rivets, this sheet and this sheet. It's actually a sheet, if you can believe me. Okay, so the two sheets are joined by these rivets here. Of course, actually. Right, so you got, bolts going in, right? Okay, so maybe there are more. Anyways, so these are the sheets. They're joined by bolts, right? By rivets or bolts or fasteners, same thing. So if one of these things come loose, let us say one of the fasteners falls down, okay? It falls down somewhere. So then you got an empty hole. You have an empty hole then. At that time, you have to apply not this analysis, but the stress concentration factor, K sub T. K sub T. So if your fastener falls off here, okay, so you're applying K sub T. Of course, things are not that simple in life. It's not a uniaxial loading anymore. It's probably going back and forth this way. Shear loads, maybe. So just like we did K1, well, okay, let me stay with this for a second. So then you have to use the K sub T because you have an empty hole, you know, where the stresses are going up. But once a fatigue crack starts there, so once this empty hole, you start a fatigue crack. So here, K sub T, but once the fatigue crack starts, then you go to your K1 or K2 or even K3. So K1 is your tensile mode, mode 1. This is mode 2, which is your shear. This is your torsion. So in all these cases, tensile, shear, torsion, this keeps changing. So this that I have drawn here for mode 1, this will be K1. For mode 2, this will be K2 and mode 3. Mode 3 is actually the simplest problem. It doesn't have all this, you know, all these complications. So, but basically that's what we do. But the point I wanted to get across for us right now, instead of getting in too much into fracture mechanics, just for our work, as long as it's an empty hole, K sub T, and then once the fatigue crack comes, then you have to go to analysis of K1, K2, stress intensity analysis. Okay, this is large concentration stress. Huh?
From the aircraft, and we are having three types of the forces: tensile, shear, and torsion that will be acting on that hole.
I'm saying it's possible. Yeah, it's possible. What I'm saying is, if you have a tensile mode, then you will use the expression for K1, because 1 refers to mode 1. But if there's no tensile loading, if it's all shear like this, back and forth, then you will have to use K sub 2, that's shear loading, shear mode. And if you have a torsional, then you have to go K3.
From this general, we came to know that when aircraft will be failing, if one rivet.
Well, one rivet may not cause the failure, but all I'm saying is in theory, that's what you have to do. But a few rivets fall, yes, then you have a problem.
From this, we came to know that when aircraft lag may fail.
Yeah, yeah. So if you have a corrosion problem, like those guys have corrosion problems in their maintenance sometimes. So if the corrosion forms between these two sheets, which is very common between these two sheets, if corrosion forms there, yes, you're going to start riveting, rivets popping out. They'll start to come out. And then you're going to have a problem. Yes, yes, absolutely. Absolutely. Yes, stress analysis guys, load analysis will do it, yeah. So you brought it to a point where I can just go and introduce one more new concept, just for the next, whatever we have, 15, 20 minutes maybe, right? I know it's been a long day, it's been a long day, right? Have mercy. No, no mercy. He's saying no mercy. I'm okay, you guys, I'm worried about you. I slept pretty good, actually. You're going to say something? No, okay. So, the good thing is this. let us stay with mode 1. We're having enough trouble with mode 1. So let's stay with mode 1. If you bring in mode 2 and mode 3, we'll be in really trouble. Although it's simple analysis, but I think combining the modes is the tough part. It's very difficult to do combined mode testing. We just started to do combined mode testing when I was working. Okay, of course, I left 2 years ago. So now they're working combined, like mode 1, mode 2 combined, mode 1, mode 3 combined loading. So testing some of this is not that easy, actually. It's a little difficult. Combined mode loads is tough because you're putting tension, and at the same time you're doing this also. It's a little bit difficult. You need a very good technicians to do that. I don't know if you have good technicians in your labs, but that's the most important person in any lab is the technician. You need to have a very good technician to be successful in a lab. So you always have to look for the best guy possible. He can make or break your lab. Yeah, that's my advice to guys who are working in the industry. Try to be nice to the technicians, but they are the most important people. You should take them out for dinners, lunches, buy rasgullas or whatever, Oh, they're very, very key. If you have a good technician, they will do a good job for you. Some of this testing you need somebody very good. It's not easy.
You have talked about stress cohesion.
Yes.
Yes.
Yeah.
You were talking about some RR process.
You mean retrogression reaging?
Yes.
Yeah, we can talk about retrogression reaging, yes. I was going to talk to that. Yes, yeah, absolutely. That's a good point, actually. Yes, very good, yeah. But I have to talk to them before that aging process, yeah, absolutely. Very good. Yeah. When you said RR, I immediately thought about the retrogression reaging. Yeah. I'm glad you're in this meeting. I'm very glad. If you're not there, I will be speaking all lies and getting away with it. He's trying to check me, make sure that I'm speaking all truth. Yeah. He's watching me. Okay. So the good thing is this, right? We have K is equal to sigma. So you never want to forget this equation. This is a very simple equation. Stress intensity, stress, and crack length. Very simple, right? So this is all, we talked about fracture toughness and all this stuff. If I put a little symbol in front of it, delta K is equal to delta sigma. This is all what you have to do for fatigue. This is fatigue. This is monotonic. Or monotonic or rising load, maybe rising load. Like, for instance, fracture toughness. So this is for fatigue. So basically what we are doing here in the fatigue load is, I'm not going to dig deep into it today, but just introduce. So simple, again, in the fatigue it can get very complicated. We'll stay with a simple load, bless you. So simple loading, sinusoidal loads, simple. We will not use the real aircraft loads or the real helicopter loads maybe, which is much more complicated. Much more complicated, difficult to solve. So we'll stay with this. But there are solutions to this. Okay, so we're staying pretty much. So this is our let us say zero load. So this is my zero load, and here is my maximum load, and here is my minimum load. Okay? So my delta P is basically P max minus P min. So basically that's the fatigue load that I'm putting. And everybody knows what fatigue is. Even though I'm below the yield strength, you know, it will fracture after some time. Even though I'm below the yield stress. And that's the danger, right? That's why fatigue is such an important problem, because you're way below the yield stress. So this is my material I'm working with. So there is my yield stress. About, you know, we don't have to be exact, but there is my yield stress. I'm below the yield stress. I'm maybe here somewhere. But if I put sufficient cycles, it will eventually fracture, right? It will eventually fracture. Just trying to see if Trump is calling me from North Korea. No, this is not. Okay. Okay, so after a certain number of cycles, it will fail, right? That's the danger about fatigue. Okay? So this is the fracture mechanics equation for an infinite plate for fatigue. So I have a same thing. We have a crack, and we're putting sinusoidal loading, for instance, or you can put a square load. You can put any kind of triangular wave. You can have a triangular waveform if you want, right? Or you can also have you can put a sustained load at the P max. You can hold the load for some time and then start all over again. Okay? It is a very important waveform, actually. We will talk about that a little bit later on. Okay? What happens when you have a maximum load for a few minutes there? Now, the important thing about fatigue is so you can have the waveform like this. You can also have the waveform just zero load. This doesn't have to go through zero each time. So here you have a, let's say, plus 100, minus 100. This is 0, 100. But you can also have everything above 0. Plus 100, maybe plus 20. The both are plus. Here they were plus and minus. Here both are plus. That is also fatigue, which will cause damage. And here the delta P is obviously 80. Here it's 200. 100 minus 100, you know. So if I'm doing a fatigue test, just like any other test, the most important parameters I should record are what is my R value that I used. R is defined as, I'm going every which way. Okay, let me, P min divided by P max. Minimum load by maximum load is my R value, or ratio, minimum divided by maximum. So in this case, minus 100 divided by plus 100. So my R value is minus 1. In this case, it's plus 20 divided by plus 100. 1/5, right? 0.2. So here my R value is 0.2. Here my R value is minus 1. We should always report what is the R value. Okay? Always. The next thing you always want to write is, what is the frequency at which this load was applied? Was it, the most common that we use is 30 hertz, 40 hertz, 50 hertz, up to 100, most commonly. But we should always write that. Of course, if it's a room temperature test, you can put in the figure caption, room temperature test. But if it's a high temperature test, you definitely have to put what the temperature is. That's a, that's a no-brainer. That's obvious, right? It's a high temperature test. Basic, okay, that thing is, that thing's gone behind. There's no way you can get it. Okay. I know I mentioned this just because we were here, but we will revisit this a little bit later. But let me continue with fatigue. I'll tell you what the difference is. So let me continue with high cycle fatigue. So before I even go there, actually these slides I have on that thing. I can actually put them back. High cycle fatigue, low cycle fatigue, fatigue crack growth. Okay. We will print those, we'll print all those slides, give it to them tomorrow. Yeah. Fatigue crack growth. Huh? Yeah, yeah. Yeah, shall I bring them down? Yeah. Okay. Yeah, we needed that board for something, so we're done with that. Oh, shoot. Okay, where are we? Oh, okay. Time are we going to do? 5 to 5? We stop at 5, right? Huh? 5? Or 5:30? 5? 5. So we got, okay. I lost the cap. Am I supposed to hit the button here, right? Ah, okay. Oh. That's okay. I don't care. Well, anyways, what we just talked about, the mode 1 crack propagation. So there is the fraction mechanics equation for a center crack panel. So we'll give you these tomorrow. And there is the F of AOW. F of AOW for the compact tension geometry. Okay, it's right there. We talked about this. So there is the fracture toughness, load displacement curves. There's a K sub Q, talked about that. Standard test method E399. So there are a lot of, design has to be done properly, the clevis design and all that stuff. The cracks. For the bend specimen, calculation of the, K calculation for bend. There is your elastic plastic fracture mechanics. And there is a difference, there is the thickness criteria for the 25 times J1C divided by sigma y. We can talk about this again over and over later on. Let's just go through just understanding the whole overall big forest. And there is your fatigue crack growth curve, which we just started to talk about, but we haven't yet. Okay. Design allowables. Okay. Parameter. Okay. All right. So let me go to the fatigue one. Okay. So yeah, there we are. So again, there is a ASTM standard for this also. Constant load amplitude. Typically load control, yeah, R is equal to -1 in this case, fully reversed. So in the high cycle fatigue load, which is also called as load control test. Okay? So again, the literature problem. I call it as a problem because it is a problem. Okay? High cycle fatigue is the same as stress control fatigue, same as load control fatigue, depending on who's writing the paper, is a mechanical engineer or a materials guy, or maybe civil engineer, who knows. So same terminology. But the problem is, but the point is, we're staying below the elastic limit. Okay? It's all below the elastic limit. 20 to 30 hertz typical. Okay? ASTM does not want more than 2 degrees C change during the test. Otherwise, the test results will be affected.
Maybe the examples for R is equal to -1, R is equal to positive, some positive.
R is equal to -1?
Any examples where
Yeah, yeah.
the R is equal to positive it is.
Right. Yeah, yeah, comparison. Comparison, yeah. Okay.
Is there any examples?
Yeah, yeah, definitely. Definitely. Yeah, I'll show you. Yeah? Okay. Yes, absolutely. I'll come to that. I'll come to that. So what I want to, okay, so this is all good. This is all fine. Okay, no, don't worry about the machine that you use. I think the machine, these are all old machines. I just put up there just for the heck of it. But most of the new machines are all servo hydraulic closed loop testing machines. That's what you're using, right? MTS or Instron or whosoever that is. Most of them are, you can do bend fatigue, you can do uniaxial fatigue, you can, depending on the application. That's the most important thing, right? But in the last few years, I don't know how many years it would have been, maybe 15 years? Time is going by so fast, I'm losing touch with time. We are doing ultrasonic fatigue now. Because what is happening is, especially for the engine components, okay, so one big difference between the airframe and the engine is, in the airframe, you can have this long cracks and still be able to fly. You can still fly with cracks this big, no problem. Well, I mean, unless you have that in the fuselage, then there's a problem, I mean, if it goes through the fuselage, then there is a problem. But if you have a crack on the outer, I showed you, one sheet, second sheet, third sheet, like that. But if the outer sheet, the one that's, you touch the plane out from the outside, that's the first sheet. If there's a crack there, it's okay, nothing will happen. But if the crack goes through all the layers, then you're in trouble. Then your internal pressure, your oxygen supply will be affected and people will die, essentially. That's what's going to happen, right? But in the engine, even if you have a small crack, that's very dangerous because the parts are rotating so fast, 30,000 RPM, and the crack growth will be much faster also. So we have started to do, when I say we, the community, and also, AFRL, Air Force Research Labs, but ultrasonic fatigue system. That means you're running the test at a 20 kilohertz, 15 kilohertz, like that, 30 kilohertz, that type of frequency. You can just, if you have a calculator, you can just see, if you want to run a 10 to the 8 cycles, like 100 million cycles at 30 hertz, how long will it take? Can you divide that 10 to the 8 by 30? How many months or years would that be? So I want 10 to the 8 cycles, and I'm running the test at 30 hertz. And it will take me how many? So that will be seconds. Okay, divide that by 3600. That will be hours. So that will be divide by 3600. Divide by 24. That will be so many days. Huh? See, how many days? 38 days. So if I want 10 to the 9, it will be more than a year. It will be more than a year if you want to reach 10 to the 9 cycles. So normally what we do for aircraft is we run 10 to the 7. That's good enough. But for engine, we are going more and more because, well, hopefully I'll have a curve there, because the curve that we established previously is not holding good anymore. We are seeing that if when you run longer, the curve is still going down further. So we are running the community. What I mean, community is running higher frequency tests, so we can go there and see what is going on at the longer life cycle time. So we're going to ultrasonic fatigue for that. And these are special machines that are becoming available slowly. But right now, people are constructing the instruments themselves. We had a very good, like I was talking about technicians, in the AFRL, we had one of the top guys in the world, maybe, who constructed this machine. Did you say something? Huh? Cut it off? Okay. All right, we'll cut it off here, and then we'll pick it up tomorrow.